All right, good morning, everybody, to this fourth day of conference. It's my pleasure to introduce Gero Friske from the Technical University of Munich, and he's going to speak about the theorems of Rockefeller and Düsseldorf from a PDE point of view. Please.
Yeah, good morning, everybody, and thanks, first of all, to the organizers for this wonderful meeting. It's great to be here. So I explain the title of my talk on the first slide because it's easier once we've seen some things. So one of the ways of checking optimality of optimal plans is by duality. So when strong duality holds, you get a constraint on the support of the optimal plan, etc. And so that comes from quite general principles like, for example, Fenchel-Rockefeller duality. On the other hand, there's an alternative approach which works only for OT, so it's less robust when you entropically regularize or do things like this. But it's very nice for OT because it works on rough spaces for rough costs and things like this. And so this is this cyclical monotonicity approach. So if you have probability measures, so in my case, I'm interested in nice spaces, so compact subsets of RD and say continuous costs, then a plan minimizes the OT problem with marginals mu and nu, if and only if its support is C-cyclically monotone. And the definition is quite old. So I used to think it was due to Smith and Knott 92, but then Guillaume taught me recently that it's really due to Rocher in 1987. So Guillaume, are you here? No, now he's not here. So oh, he is here. Yes. So the definition is that a set in the product space is CCM if and only if the cost sum of some finite chain of points goes up when you reassign the y's to different x's. Yeah, so this is sort of intuitively quite clear. And so the difficulty with this are the three quantors sitting here. So there is a for all, and a for all. So the first for all is for all finite subsets of gamma. The second is less bad. It's for all cyclic permutations. So originally for all permutations, but by the structure of permutation that each permutation decomposes into cyclic permutations on disjoint subsets. You can use just cyclic ones here. And then even worse, so for all cycle length L. So that makes it tricky. And so, yeah, the proof of the necessity is elementary. I talk about on the next slide. The converse is less easy. And so, so in particular, we can ask about these three quantors sitting here. Do we really need all cycles in this? And that's, I think, a question that hasn't been addressed, and I got interested in it from the point of view of computational methods, because so for a long time with my group we have been developing numerical methods for computing high-dimensional multi-marginal OT problems. And so we have a nice algorithm I'm going to show you. Of course, I cannot resist showing it to you regardless of the title of my talk. So I will talk about this. And so we recently found out that both to understand or speed up the algorithm, it's important to find CCM violating cycles given a temporary candidate for optimal plan. And so then so this paper is in Math of Computation 2024. So where we yeah, and so then in particular, so when you come from PDEs, so when you maybe come from discrete systems, you think that having some large discrete parameter like little l is kind of bad because it makes things worse. When you come from PDEs, you think exactly the opposite. You think large L should make things better because there should be a nice continuum limit where everything becomes much easier. Yeah, so we're going to look at this parameter here. So now, okay, so here's a short slide on why the fact that CCM is necessary for optimality. So that's elementary. So take a set of 3 points, let's say, in the support of some plan. And then, so you look at the cyclic permutation. So you move some mass from x1, y1 to x1, y2, some mass from x2, y2 to x2, y3, and some mass from x3, y3 to x3, y1. Okay, and so this gives you a trial function. So the way you cook this up rigorously is you just take a small ball of size little r, and okay, because the points are in the support, so if you look at a small ball around that point and cut the plan there, so that charges, so that has positive mass, you normalize to 1. You compute the marginals of this guy here, and then you do the following variation. So you deplete the plan by a small amount of these gamma epsilons, so that stays positive. And then you add just the product plan, but shifted. So that's your trial plan. So that has the same marginals. And then you do the elementary calculation, 0 less or equal 1 over epsilon new cost minus old cost. So that's by optimality, you get this inequality sign, and this converges for continuous cost to this value here. Okay, so that's that. So this is really not the difficult thing. So it's the other direction that's kind of interesting. So yeah, of course all this stuff is very well known. So I have another very well known thing. So you can the opposite limit of the one I'm really interested in is the ultra short cycles. So it's L equals 2. So in this case, C cyclical monotonicity is called C monotonicity, so cycles of length 2. And then the nicest case is always the quadratic cost. So if you have this cost inequality and you plug in the quadratic cost, then the squares cancel on the left and the right, and you're left with inner product terms. And if you rearrange them, you just get naught less or equal y2 minus y1 dot x2 minus x1, or if your plan is a graph of the map, which is the case we'll be mainly interested in, then you just get this condition here. So t of x2 minus t of x1 dot x2 minus x1 bigger or equal to 0. So of course this is just monotonicity of the map. And so CCM for cycle length 2 is equivalent to monotonicity of the optimal map. Okay, so all this so far is very well known and in pretty much every book on OT. So now this was maybe known to early pioneers. I suspect it was known to Rockefeller, but he deliberately disguised it in his papers because he wanted, I mean, this was the heyday of Bourbaki, and so he wanted people to learn the new math of non-smooth functions. But I would imagine the first people who thought about these things would make these calculations on a sheet of paper and then carefully put them away so that nobody finds them. So here's a calculation in the continuum limit for the quadratic cost. So what's the meaning of CCM? So the kind of opposite limit is not an arbitrary cycle that lives in a nasty random position, but in my universe coming from PDEs, you look at nice smooth cycles. So we look at a smooth closed curve in the support of the source measure in RD. So we take a parameterization with mesh size h. So you get a bunch of points that sit here with the distance in parameter space being h, and the alpha of ti would be the xi's. So now let's see what happens when you write the CCM inequality. So CCM applied to the cycle is here. So naught less or equal cost sum with the new assignment of y's to x's minus cost sum with the old assignment of y's to x's. So that's the CCM. Okay, so now by these kind of calculations with canceling squares, this has a nice structure. So you get xi minus 1 dot yi, and then so if your plan is induced by a map. So you have a t of xi here, then xi minus 1, and then I multiply and divide by the mesh size h, so by the grid spacing h, and then I see something nice, because what's sitting here, so the h is basically a time integration, so it's the delta t. This here is a difference quotient of the axis, so that's precisely the derivative of the parameterization. So this term goes to alpha dot of t, and here you have t of alpha t. So what I'm saying is that this CCM difference is basically a Riemann sum for a line integral. Yeah, so that's my claim here. So, and this Riemann sum for line integral is much nicer than just a Riemann sum for line integral, because we know from elementary facts that this is independent of the parameterization. Yeah, so this is just the circulation of the vector field T around the curve C. So at the end, I discover an intrinsic quantity that is independent of the parameterization of the curve. Yeah, so that's just the circulation of this vector field. And so you know, in this continuum limit, so again, and you get this inequality 0 less or equal. So now I can analogously change the orientation of the cycle. So how do I do that in the discrete? So I assign xi to yi minus 1. So I go in the other direction, and then I get not less or equal minus this circulation, just by using the cycle with the opposite orientation. And therefore, therefore I get a very nice result in the continuum limit. So CCM is equivalent to circulation around all closed curves is 0 of the vector field. And so so we learn in calculus that this is equivalent to the curl of the vector field being 0. And then if you are in a simply connected domain, the curl being 0 is the same as the vector field being a gradient. So that means by this simple and very, very straightforward calculation on this slide, which I haven't seen in books, but which I suspect Rockefeller knew. So we discover that CCM is equivalent to the map being a gradient. Okay, so that's the opposite limit. Now, so now let me come back to the question initially posed, whether we really need all cycles in the CCM optimality. And so now let's look at the quadratic cost. So in my talk, I focus on the quadratic cost because it's nicest, but you can do similar things for more general costs, of course. So let's look at CCM and Brenier's theorem. So we suppose we have an optimal plan, which is the push forward under a map. So then by the elementary argument, the support of this plan must be CCM. That was the elementary one-line calculation I showed. So then we milk it for L equals 2, the ultra-short cycles. We get that the map is monotone. And now I milk it in the continuum limit of cycles. So and here I need to do a bit of assuming. So the circulation, if we don't want to go into heavy analysis of under which conditions it's still what is minimally needed for making this well defined. So let's suppose here that the map is continuous and the support of the source measure is simply connected domain. Then the continuum limit gives you that T is a gradient. Yeah. And in fact, so there's an elementary fact. So when you have a gradient, then monotonicity of the map is equivalent to convexity of the potential. Yeah. This is only true when you have a gradient, but when you have a gradient, it's elementary. And so from these considerations, we get a nice viewpoint of Jan's theorem. So optimal implies gradient of a convex function. So that's one way to understand this. And okay, so that's interesting. But what's even more interesting is to go now the other way. So if we now go the other way, we know from Brenier's theorem that so T monotone and T gradient is also equivalent to the plan being optimal. Okay, and now this is like the really a main point of this talk. So that means that for optimality, we don't need all cycles. We just need those cycles. So the tiny ones, the ultra discrete limit, just cycles of length 2, and the smooth, nice continuum limit of nice cycles. And that gives you back. So by the other half, we don't need all the cycles in this Röschendorf theorem. And so here's a more precise way of quantifying these cycles. So now it gets a little less trivial, I hope. So yeah, maybe you were happy that I was not so non-trivial, but I'm not sure I am happy if I'm too non-trivial. But okay, so now we're going into yeah, really. So here's a corollary of these considerations. It's a result, I call it, it's a kind of lean Röschendorf. So it's like Röschendorf's theorem in nice settings where the for alls have been really reduced. Yeah, so you have much fewer cycles. And so it's quadratic cost. We assume there is an optimal map. So for example, guaranteed with absolutely continuous source measure. And we assume here that the optimal map is continuous and the source domain is a closure of something simply connected. So, and we give ourselves any threshold epsilon bigger than 0. So then optimality is equivalent to the CCM inequality for the following two classes of cycles. So we need all cycles of length 2. So that gives us the monotonicity. And so now here, these cycles that are associated with the curl. So let's go a little more quantitative. So how many cycles do you need to control the line integral of to control the curl? Yeah, and so very special cycles, I claim they're enough to control the curl of T. And so here is the picture of these cycles. So you just need boundaries of axis parallel squares of size less or equal epsilon. Yeah. So first of all, you save on the large cycles by partitioning the interior into many small cycles. So this is the usual kind of theorems, how you prove the divergence theorem or Stokes' theorem. And then, you partition a large square into small squares, for example, and then the contributions to the circulation from the boundaries cancel because you see them twice with opposite orientation. Yeah, so you can go from large to small cycles. And the second thing is you can also fix the orientation a lot, because why? So these very special cycles that control curl T, they're here. So in okay, so in 3 dimensions there's an anomaly because somehow the differential forms of size, so of order 1 are basically canonically isomorphic to the ones of order dimension -1. Yeah, but in general, so you can think of the curl T as the antisymmetric part of the gradient map of the Jacobian of the vector field. So you subtract the transpose, and so this is basically so dti dxj minus dtj dxi, but that is the limit as epsilon goes to 0 of 1 over epsilon times the circulation like around a small on a small square. Okay, and so that fixes here the orientation of the cycle. So you can quantize the orientations. So let's do a count. So suppose we are now doing something associated with discretization. So instead of discretizing map and plan and then looking at duality arguments for the discrete problem, we could also discretize the CCM condition. And so if we replace X by uniform mesh with n points. So the number of cycles, so this for all in Rüschendorf's theorem is terrible because it's n factorial. So that is combinatorial in the fineness of the discretization. So computationally, that's useless. But cycles of length 2 is much better. So there are only n squared of them. I mean, n source points, n first points, n second points is order n squared. And so then you might think that the continuum limit is kind of worse than the ultra-discrete limit in terms of complexity, but surprisingly it isn't. It's just as good. It's even a little bit better. So there are even fewer continuum limit cycles than there are ultra-discrete cycles. So if you count so I ignore the size here and just count to get an upper bound the axis parallel squares in d dimensions. So axis parallel means spanned by 2 of the basis vectors. So there are order d squared of them in d dimensions. Yeah, so that's the factor d squared here. So that fixes the orientation. And then in an axis parallel square, I have basically 2 points. So one is the base point, the other is along the diagonal. So the base points, there are n base points. If you have n discretization points, each discretization point can be a base point. But the square, it just points in the direction of a diagonal in 2 dimensions. Yeah, and so that's exactly square root 2 times n to the 1 over d. Yeah, if you have n grid points in d dimensions, on each direction is n to the 1 over d. So Filippo. Yes, yes. So yes. But I mean, here I cannot do it because I mean the discretization size is sort of 1 over n to the 1 over d is basically the best. Yes. Okay. So yes, that's theoretically true. I could do that, so I could save a little bit there. But to approximate the line integral for a smooth map, it might be nicer to have a few small points and then extrapolate. Yeah, it's just for robustness. It's an upper bound. So I'm not sure how good. So yeah. Yes. So in principle, you could remove the 1 over d, but I'm not sure whether it's numerically a good idea. So for the approximation. Okay, but in any case, we see, so the main offshot, regardless of whether we save on the 1 over d or not, it doesn't make much difference because we have order n squared anyway. So it's basically goes from n factorial to order n squared. So I think that's a useful thing. Okay, so now let me get to so there is a very nice formula by Rockefeller in which has to do with passing from a CCM set to some kind of potential function. And so this construction, certainly to me, when I first read it, it was very mysterious. So this is kind of came out of my own efforts to understand this formula. So once we are in a nice setting of RD and we have a continuous vector field. So there is a standard way we learn in calculus how to find the potential of a curl-free vector field. We just use a line integral. So in physics, it would mean I compute the work along a path to get from the first to the second point, and then that gives me the potential energy. So to compute the the potential function, I fix some reference point x0, and then I do the line integral of the vector field. Now this time not along closed curves, but now I use open paths that connect x0 to the target point x, where I want to evaluate. And so, so if the domain is simply connected, this integral is again, it's independent on the choice of paths. So that's again one of these nice things in vector calculus, that the right things are independent on the choice of paths. So, so you do this open path line integral, and you rewrite it again as a limit of my cost sum, so t of xi dot xi plus 1 minus xi. So that was the Riemann sum that goes with this line integral. Yeah, so now we kind of do this. So on the other hand, so this is a sort of nice expression for the W, but I have to pick specific paths here. So for example, in a convex set, I could just take the linear path going from x0 to x. Now, on the other hand, now let's not do this for a general vector field, but for an optimal map for the quadratic cost. So then I have a lot of extra knowledge about the map. And so the knowledge I'm using in this elementary calculation is so that the t of xi is the gradient of the potential at xi dot xi plus 1 minus xi. So that's, of course, clear when you want to, when you have any potential. And but now we know that the OT map has the advantage of being the gradient of a convex function. And so that gives me an inequality for the Riemann sum, which is very nice. So the inequality is local for each contribution to the Riemann sum. I can estimate this thing by the cost difference. Yeah, so this is just the usual thing that the convex functions lie above its tangents. So, and then you sum up. And so this is a telescoping sum. So everything cancels except the first and the last contribution. And so you get that the Riemann sum that approximates my potential function is bounded above by the potential function itself. And so that is very nice. So I have two things now. I know I can reach the potential by taking the limit of choosing some special path and some discretization. So I can reach the Wx by such Riemann sums. But I'm always, so the Riemann sums are always less or equal the sum. And so therefore you get the formula that you can rewrite the potential function as a supremum of these Riemann sums. So, and I'm writing it here. So now I'm introducing back the quantizer for all. So you take the sup over all discrete cycles of length, discrete paths of capital N, where the last point is basically x, so the point where I want to evaluate the potential. Okay, so and now, so this formula is now nice. So we've derived it by really coming from the smooth case and using the line integral interpretation of the CCM inequalities. But I mean, once we have it, so I think of it really as a tool to get it and to understand where it's coming from. Once I have it, so this definition makes sense much more generally. So this is exactly the Rockefeller's construction. When you have a general CCM set gamma, and you want to show that it's contained in the subdifferential of some convex function. Yeah, so that's exactly the formula you use, and so so Rockefeller he did not read the book by Ambrosio Gigli Savare. I mean, all of them are here, so it's fantastic to talk about this. So the one thing he did not realize is that his sums in his formula involve differences between base points, but that forces you into a vector space. And so certainly in the Rocher and Rüschendorf paper, they're working with general costs, and they realize, so they add back in the squares that I deleted out at the beginning. So you can replace all these things by cost differences instead of base point differences. So it's good to keep the xi squareds in, because then you can rewrite everything in terms of cost differences. And for cost differences, you just need that the target domain of the cost function is a vector space. Yeah, so cost differences are much simpler. So that works then in a metric space. So by rewriting with cost differences, this analysis works in the metric space, and was used to great effect. So it's one of the many nice uses in metric space that is nicely explained in the green book by Ambrosio Savary. So Rockefeller was missing this fact because he was coming more from like vector space theory, and then that was understood later. Yeah. Okay. So that's my take on these things. But so certainly just to summarize, so by a complete and utter coincidence, this discussion I gave so far, it happens to be section 6.9 of my TU Munich lecture notes that finally came out like a week or so ago. So at SIAM. So if you so for you, this comes maybe too late because you learned optimal transport in lots of other ways, but maybe your students find this notes useful. Okay, so so now I come. So the second part of my talk, I want to talk briefly about my motivation, how I got back into CCM. So in fact, the first paper I wrote on OT was heavily using CCM. So this was on the Coulomb cost and many years ago. But then I sort of changed religion and followed the duality approach for a long time. And then this numerics led me back into CCM. Okay, so I think I forgot to mention one thing since Luigi De Pascale is here. So there's a very nice recent survey by Luigi and Anna Causamo, and I didn't know the third author, Cesar, yeah, on 60 years of CCM. Essentially. So it has also wonderful counterexamples what happens in the rough case. So when you do optimal transport with rough costs, maybe not continuous, maybe not even lower semi-continuous and rough spaces. So highly recommended. So okay. So now the computational OT. So if you numerically compute an n marginal optimal transport problem, so you minimize a cost summed against the plan, and the plan is a function on the product of n spaces. And the plan, so the density of the plan with respect to counting measure on the mesh points is non-negative, and you have n marginal conditions. And so the fundamental problem there is the curse of dimensionality. So if the marginal spaces come with L grid points each, then the product space comes with L to the n grid points. And so you have an n, which is the number of marginals in the exponent. So it's a classic case of a curse of dimensionality. And so the starting point, so you may think it's hopeless to discretize these things, but the starting point we thought about with my students, with Daniela Vögler and Max Panker, is there is, on the other hand, so the multi-marginal case is nice because of a high degree of sparsity. So for any cost, this discrete MMOT problem has an optimizer where the support size is bounded by the sum of the marginal sizes, not the product. So it's bounded by the sum, not the product. So it's not exponential, but it's linear in the number of marginals. So multi-marginal problems have very sparse optimizers. So the proof is very simple when you know Dubin's theorem. So it says the following: if you have a compact convex set in a Banach space, and the set is an intersection, and you form the intersection of this compact set with n hyperplanes, then every extreme point of the new set is a convex combination of at most n plus 1 extreme points of the old set. So So in terms of extreme points, intersecting with hyperplanes is not bad because it pushes the number of extreme points up by 1 for each hyperplane. So what counts, what's important is the number of constraints. And so in the multi-marginal case, so the number of constraints is proportional to the sum of the size of the marginal spaces, because for each marginal space you have a marginal condition, and that condition has to hold on every marginal grid point. And so that's where the sum comes from here. And then, you know, if you count correctly, some of the conditions are redundant because the normalization you need only once. So you overcount a little to get the exact count. So, and then in this case, you apply this to the simplex of probability measures on a large set, but the extreme points of that are just the Diracs. So in this case, if you start from the simplex of probability measures on a large set, it's a tiny so you have only one extreme point. Sorry, you have support size 1 for the extreme points, and so then that goes up to this. Okay, so and then so when you want to use the sparsity in algorithms, it's not so clear what you do. So but the basis how we started, so this algorithm is called column generation, goes back to Danzig. It's not Danzig, it's Danzig, I'm sorry, and Wolf in the 1960s. So so they suggest, instead of full OT, to solve iteratively OT on an initially small subset. So you restrict the problem to a small subset, and or equivalently the dual has fewer constraints. So in the dual problem you have fewer constraints. In the primal problem you have fewer unknowns because your plan only lives on a subset. And then you update the subset by finding the point that violates dual admissibility most. So the good Kantorovich potentials should be admissible, so they should satisfy the admissibility inequality at all points, but here they only satisfy it in the small subdomain. So you look for the point that violates that most, you add it to the domain. And so this algorithm is good when you want a sort of quick initial approximation to an optimizer in practical large linear programs. That's why they introduced it. So, and the good thing is, if this maximum here is 0, so that certifies that the plan you have extended by 0 is actually optimal for the full problem. I don't have time to explain why, but it's not difficult to understand. And then but the problem for MMOT with this are two things. First of all, this pricing problem is not surprisingly is NP hard, because you have to search over an exponentially large space, so you can't do that. And the second thing is that the convergence is only guaranteed after your set became as big as the whole space, which is what you want to avoid. So that's why we introduce a variant that fixes this and can exploit the sparsity. So the main difference, we call it genetic column generation, again introduced with my colleague Andreas Schulz from discrete optimization at TUM, and my former PhD student Daniela Vögler, and my current PhD student Max Panker. So you solve OT on a globally small subset. So you keep the size of the subset, the order of the support of the sparse optimizers, and you just give an extra factor 3. So it doesn't have to be 3, it could be some other constant. In practice, we use 3. And so then you solve this reduced problem, and then you update the subset in a better way. So it's a kind of genetic update. You pick a random new point, a random point in the support of the current optimizer. You change it in one coordinate, and you wait until, so you repeat this until you find some point which violates dual admissibility. Then you add the point. And also you have to remove points. So how do you remove points? You do this when your set reaches the threshold. You remove you also have a genetic removal rule. So you remove those points that have been unused the oldest. So the ones that have been the longest not used by the temporary optimal plan. So that's a kind of learning in this algorithm. And so the fact is that this algorithm really works wonderfully for large problems. So here's a classical, so it's quadratic cost in 1D. So you initialize with the wrong plan, and then, so here you see the evolution as a function of number of iterations. So here's the plan, converges to the optimizer, and here's the Kantorovich potentials, they converge to the optimizer. So initially there's noise, so it's a noisy algorithm, but it automatically self-down tunes. So there's no annealing, absolutely none. It self-down tunes the noise. So this is great. So, and we always observe exponential convergence. So here's a log scale, and that's the cost. So here I'm showing some synchron for comparison. So it's initially much faster, but of course you don't go beyond the accuracy that is set by the synchron parameter. So if you want something quick, like you often want in data science, use synchron. If you want high accuracy, as you do in the kind of physics problems Simone de Marino was talking about yesterday, Coulomb cost, for example, then use this one. Okay, so the points here were, so we preserve the sparsity, and the updating, I should mention, is partially inspired by machine learning ideas in adversarial learning, because the proposal step of the update is something like an SGD step for the generator, and the acceptance step uses the dual, so that acts as a critic. So for those people who know adversarial learning. And it's sort of very simple, so just solves small LPs, and the noise is down-tuned. So here's some other examples. So here's MNIST digits, we barycentered them, so that's 10 to the 28 unknowns, converges wonderfully. Here's a Coulomb example, converges wonderfully. So here we did also the scaling with system size, so we used the increasing sequence of larger and larger problems, where the number of particles increases, so that's a log-log plot, and the number of steps you need in the algorithm, micro steps you need, it just is a line with a low slope, so scales polynomial, and the number of unknown scales exponential. So at the end, with 10 to the 4 steps, you do a problem with 10 to the 30 unknowns. And so recently we also did this for the Wigner crystal with 30 electrons in 2D on a 30 by 30 grid, hopefully out before Christmas. So it's 10 to the 56 unknowns. Again, it sort of works just fine. So and the end state we get is called the Wigner crystal. So this is what you expect in the Coulomb problem Simone was introducing yesterday. Was predicted in 1934, but people are still interested. So it's in 2019 was the first experiment on this in 1 dimension. And so here in the algorithm, this is a slightly smaller example. You keep iterating, and at the end, you converge to. So here I'm just showing, I fix one point, and conditioned on where this point is, I show where the other particles are. So it really nicely, out of initial very noisy situation, it finds the right thing. So again, exponential convergence. So now I want to go back to CCM to close up. So for n equals 2, so for 2 marginals, we have a convergence theorem. So for any cost, any marginals, any feasible initial subset, this algorithm converges with probability 1 to a global minimizer. So that's not trivial, because we did the support constraint, so it's an L0 constraint on the plan. So the L0 norm of the plan stays bounded, so that's not makes the problem non-convex. But you find the global minimizer. So, and the proof, I mean, I don't have time to go through it in detail. I want to finish on time. So in the proof, you kind of see that the algorithm, after a number of steps, which is proportional to the sum of the marginal space sizes, not the product, it finds a cycle which strictly lowers the primal cost. So this analysis is short. I don't have time to talk about this in detail, but it's in our paper and it fits on one slide. But the key point is that you can, using CCM, you can estimate the number of steps needed to find a CCM violating cycle. And the number of steps you need is proportional not to the size of the product space, but to the sum of the sizes of the marginal marginal space. So that's the non-trivial thing. So bounding this rate. And so then, yeah, and so we're trying to do this for the multi-marginal, but I think my time is up, so I finish here. So the summary is you don't need all cycles in Rüschendorf's theorem, and that helps us to understand, and possibly we are trying at the moment to speed up the algorithm using this idea that you don't need to find all cycles. Yeah, thanks for your attention.
Thank you very much. Are there questions? Yes.
Okay, thanks a lot. That was a really nice, interesting, very clever method that you used. I have two remarks. The first is historical, and been working for more than a decade with Rüschendorf, so I would be very glad to see your talk. And but I think that the same result on cyclical monotonicity was developed by the group of Gango McCann during the same years. So Robert is there, so maybe we can ask me. I think that it was an independent delivery, so stating only Rüschendorf's theorem is maybe a little bit unfair, but we can ask Robert.
Okay, so yeah, that's a very nice discussion. I'm very happy to get into this, because I mean, it's really difficult with so much literature. So yeah,
it's a lot of literature. The second remark is that in the last years we developed some algorithms for approximating optimal transport solutions where we only checked couples. And this talk is a very strong motivation why this algorithm works so well, because it just needed a little bit more on top of the couples to obtain the real solution. And the question is, you just show one slide, but in your papers there is also a comparison with very well-known methods to compute, for instance, Wasserstein barycenters, referring to Couturi and to Caulier sliced barycenters.
Yes.
How do they compare?
Oh, okay, yeah. So, I mean, okay, so you mean this picture, or?
In the paper, there is also a comparison with the other competitors.
Yes. So, okay, so how do they compare? Yes, I mean, I don't have it on this slide, but okay, so what is interesting here is, so that's kind of the exact barycenter where you solve, so the MNIST digits come on a mesh, so it's 28 by 28. So but if you barycenter a plan, so you're projecting along the diagonal. Yeah, so that gives you a finer mesh. So if I project a product mesh of 28 by 28 or 28 to the 20 along the diagonal, I get a finer mesh. And if you do so, on the other hand, so for Wasserstein barycenter, there's a couple two marginal formulation. So it's one of the great aspects of Guillaume's paper that there are these two formulations to choose. And so in the couple two marginal formulation, you can use synchron. And so you get basically a slightly blurred version of, so you get a coarser discretization of this. So and if you tune the parameter very fine, yeah, it's a pity I don't have this this slide here, but so at the end the pictures are similar, but this one is more accurate. So if you want really high accuracy on the barycenters, use this. But the synchron is quicker and less accurate. So if you want a quick and less accurate, use synchron. So that would be the message.
Right. So I just wanted to mention that I have a survey from 10 years ago where I lay out my own view on part of this, part of the first half of your talk, not obviously the last, not obviously the algorithmic part.
Okay.
All right, great.
Yeah,
it appeared in discrete and continuous dynamical systems.
Okay, so yeah, maybe we should talk about this afterwards.
Okay, great.
Thanks, Robert. And apologies to everyone I didn't, account for correctly.
Luigi.
Since many years, we have been proving that transport plans which are two-point monotone are actually transport map. And we really didn't understand very well why this works. I mean, it's clear why it works, but I am wondering whether you have a counterexample to the fact you have something which is two-point monotone, but is not cyclically monotone on very small sets. Like there is a local optimality of 2-point monotone maps or something like that.
Okay, so I mean the standard counterexample in would be this. I mean you take I mean yeah, I don't know whether it's whether you mean small. You take 5 points like this, and then so the xi is equal to the whatever, and then you reassign the xi's to the yi's and by rotating ones. So that's an example of a set. So you take 5 points in the plane. I mean the xi, yi. So this is kind of a monotone.
Okay.
Not 2 point, but I mean maybe it's not minimal in your sense.
I mean, two monotone is not optimal, and rotation are usually
exactly.
Okay, but when you look locally at two monotone maps, at the counterexample, the continuous counterexample, they are optimal.
Okay.
So
from this analysis, we always assumed that in this analysis we assumed that the optimal plan comes from a map and then went further. So we didn't try to. I mean, your question is different. So you ask, do I know a condition when it is a map? So, but maybe it would be nice to discuss afterwards. But
so time is running over, but I will leave one last question to Jan Brenier. I mean, given that it just a little bit to do with this Brenier theorem that we kind of heard about. Please, Jan.
Yeah, it's just to mention this very interesting paper by long time ago by Luis Caffarelli, who looked at the case of 3-cycle monotone map. So it's not so known, and he got some regularity result with the monotony only on 3 cycles. So which doesn't work for 2 cycles. So okay. And by the way, I would just mention also that the argument of the circulation was used. I mean, in my CPAM paper, I used it.
So you know it, of course, because you come from fluids, and I mean, the talk was not for you, Jan, because you know.
No, but I mean, this is really folklore. Yeah.
But what I'm claiming is, I think already Rockefeller knew it.
Yeah,
that's what I think.
Okay.
I also want to mention the work of Gusub and Moameni. They give a very interesting extension of Jan's theorem to finite cyclical monadicity for only up to integer k.
Yes. I also know this space. Yes.
All right. I think it's time to close the discussion. Further remarks. I mean, we have time during the coffee break or other breaks in the day. So thank you very much again, Gerard. All right. We are ready to continue with the morning session. It's a pleasure to introduce Robert McCann from University of Toronto, and he's going to speak about a geometric approach to regularity of optimal maps. Please, Robert.
Okay, right. I'm really grateful to the organizers for the chance to speak in this great ongoing series of seminars. It's nice to be back in Pisa. I'm going to talk about a paper that just appeared with Simone Brendel, Flavien Leger, who's in the audience, and Cale Rankin. And is partly based on a little bit earlier work that I did with Young-Han Kim and Michael Warren. And there's a version of my slides linked on my webpage. Okay, but we're in Pisa, we're in the Centro di Giorgi, so we should talk about calculus of variations. So let's start out by talking about calculus of variations. Here was a problem that I think was near and dear to the heart of Ennio di Giorgi, which was the minimal surface problem, hypersurface problem. So you minimize the area integrand. I'm looking at graphs U defined on domains omega in Rn. And you take a minimizer of this, and it satisfies this Euler-Lagrange equation. And when you want to analyze the regularity of minimizers, you look at blow-up sequences, and then you get an entire solution to the same equation. And in low dimensions, the only entire solutions to this equation are linear functions. But Di Giorgi and collaborators discovered that when n is 8 or higher, there are entire solutions of this that are not linear functions, and you have the Simons cone. Of course, this is codimension 1, and the higher codimension version of this problem is extremely interesting because, first of all, every algebraic curve in C2 is minimal, but algebraic curves have all kinds of interesting singularities. And Almgren, there's the big regularity theorem of Almgren says that in general, for the analogous minimization higher codimension, the singularities always have codimension at least 2, whereas in the hypersurface case, they have codimension at least 7. Right. And so let me contrast this. The integrand here is convex, and the integrand's shaped like a hyperbola. And if you Legendre transform the hyperbola, you get another convex function, which is shaped like a semicircle. And it's customary to not put the minus sign in front of it, so it becomes a concave function. Here's another maximization problem. And geometrically, what this integrand corresponds to is the problem of looking at hypersurfaces in Minkowski space. And but they should be hypersurfaces such that the Euclidean gradient of U is less than 1 in magnitude, so they're space-like hypersurfaces. And so the data on the boundary of your domain has to be Euclidean 1 Lipschitz in order to hope to have a space-like solution of this. And then if you blow up a solution around a point and you want to analyze its regularity, both the solution and the blow up on Rn will satisfy this Euler-Lagrange equation. And because this is concave, we maximize instead of minimizing. So then there's a wonderful result of Calabi from 1968, which was a wonderful year. And it says that actually any entire solution of this, provided the denominators make sense, is linear. And so in contrast to the situation when the background was Euclidean space, now that I've passed to a Lorentzian background, this holds for all integers, not just up to 8, so no singularities. But the cons are that the geometric invariances of this equation are SON, which is a non-compact group, instead of SON plus 1, which is a compact group. And of course, the ellipticity of this equation degenerates as the gradient tends to 1. And moreover, because the sphere is disconnected in Minkowski space, the pseudosphere, you have to be much more careful with orientations in this problem. But more or less, let me draw the picture in Minkowski space. So I'm in Rn1. So, and I look at the Minkowski norm is something like x1 squared up to xn squared minus xn plus 1 squared. So if I look at the points that make this vanish, I get the light cone. And these linear solutions, these space-like hyperplanes, they maybe look like this. And the unit normal to such a hyperplane lies on the set of on the pseudosphere, which is a hyperboloid tangent to this light cone. So maybe the normal to this plane lies there. And as you drive this plane closer and closer to the light cone, the normal goes farther and farther away. And so in order to prevent this equation from the ellipticity from degenerating, you need to control these normals so that they don't limit onto the light cone. So if you put an auxiliary Riemannian metric onto Minkowski space, you want to show that these normals are not too long in the auxiliary Riemannian metric. Okay. And okay, of course, the pseudosphere has a second component down here. And so I want to be careful to consider planes that are oriented so that the normal goes this way and not that way. That's one of the orientation subtleties. Great. So what does this have to do with optimal transportation? You can ask about what happens in higher codimension. So if I had instead of signature N1, if I had signature NM, you could look for space-like n-volume maximizers. And much less is known about them, but a student of Rhys Harvey wrote a thesis on this problem about 40 years ago. 30 years ago? 30 years ago, whatever. But with Kim and Warren about 10 years ago, what we showed is that graphs of optimal maps are in fact space-like maximizing in the case where these two dimensions are equal. And with respect to a suitable metric on this, where if you're doing the quadratic cost, the metric is just the generalization of this to m variables. But if you're doing some other cost, then you need to choose a different geometry. And the second result that I want to describe today, the new result, is that when you go from a Riemannian background to a pseudo-Riemannian background, and you look at these space-like volume maximizers, the maximal dimension that you can have space-like things, a sign becomes favorable, so that you get regularity where you wouldn't have in the Riemannian setting. Okay, and so this is going to lead to a new proof of the Ma-Truding-Wang regularity result for optimal mappings. Any questions? Okay, so I apologize for the next two slides, which are going to be heavy going, and hopefully they'll be, so if you are not a differential geometer, you should take them as impressionistic. But hopefully there'll be a payback later. But maybe let me draw the picture. So the picture is the following. I'm in a big space, maybe 2n dimensional, m hat, and now I have a it's m dimensional. And I have a submanifold sigma, which is n dimensional, and secretly this is going to be the graph. In our application later, this will be the graph of an optimal map. It's space-like, so the restriction of the signature nm metric tensor to this thing here is Riemannian, and I'll call the restriction G. G is G hat restricted to the tangent space to sigma. And what it means for this thing to have zero mean curvature is, so you have to look at the second fundamental form, which is, it's a mapping from the tangent, you take two tangent vectors on sigma, it gives you back a normal vector to sigma. And so the trace of this thing is some normal vector, and what it means to be maximal is that that normal vector vanishes. You have zero mean curvature. Where the second fundamental form, it measures the difference between, so you have two tangent vector fields, x and y, on sigma, and you can differentiate y in the direction x, either with respect to the Levi-Civita connection of G or with respect to the Levi-Civita connection of G hat. And one of them will give you something tangent to sigma, and the other one won't necessarily, and the difference between them is the second fundamental form. Okay. And so this is somehow the crucial lemma, the new lemma. Yes? The G is the G hat restricted to the submanifold. Right, so my notational convention is the hats are the ambient space and the non-hats are the subspace, submanifold. Right, okay, so if I take an orthonormal frame on the submanifold, little e1 to en, and an orthonormal frame on the ambient space, capital E1 to en plus 1, I get the following lemma. Take any positive definite symmetric guy on the ambient space and look at its restriction to the submanifold. Then there's a constant that's independent of the submanifold, such that you have this funny inequality between the Laplacian of the restriction on the submanifold and the Riemann curvature in the ambient space. It's a certain trace, it's a partial trace on the submanifold of the Riemann curvature in the ambient space in that direction. Okay, so I'm going to try to sketch a proof of this lemma. Okay, so there's a long computation of several pages that exploits the fact that I'm vanishing mean curvature, and it gives me this identity that the Laplacian of S in some direction, so you took an orthonormal frame, E1 up to En on the submanifold, is given by this, you were relating derivatives on the submanifold to derivatives in the ambient space. And then there's three terms. There's sort of a second order term, and there's a first order term, and there's a zeroth order term, and the second fundamental form pops up. And then there's these additional terms. And the good news is that so the second fundamental form maps two tangent vectors to a normal vector. And because the positive directions are the ones tangent to sigma, and the normal directions have negative inner product with themselves, this red term here is going in the right direction, so I can discard it. That's the good news from the fact that I'm not working in a Riemannian background, I'm working in a signed background. And okay, and so what am I trying to show? I'm trying to show this inequality, so the last term is also good news. And I claim that all the rest of the terms can be buried in the product of some constant that doesn't depend on the submanifold times an arbitrary positive signature norm of EL and EN. And so more or less what's going on is that this term has the good sign, and this term you control using Cauchy-Schwarz with epsilon. So you don't want the constant here to depend on the submanifold, but there's only one copy of the submanifold here, and there's two copies of the submanifold there, and they have a good sign. And so using Cauchy-Schwarz with epsilon, you can bury the dangerous term here with this good sign term, and you can let the non-dangerous term go into this guy, but at the cost of changing the sign of this and making it large, but large in a way that's independent of the submanifold. So C here is a large constant, but doesn't depend on the submanifold. And more or less, the rest of this is just the fact that any two norms on a finite dimensional, any two positive norms on a finite dimensional space differ by a constant. So this thing can be controlled by a product of the norm of En and the norm of El, and it doesn't matter what norm I choose, so let me choose this norm that comes from this Riemannian metric S that I picked up. And same thing with this term here, Cauchy-Schwarz. Okay, so that's the proof of the lemma. And the corollary of the lemma, this is the crucial corollary, is that now let me go to a point on the submanifold, a point and direction, unit direction on the submanifold, which maximize this S, this auxiliary Riemannian metric, so that at the maximum the Laplacian is negative or non-positive, and because S is positive, that tells me the thing in brackets has to have a sign, and I guess the sign is negative. And so the fact that the thing in brackets is negative is the inequality I wanted, that S dominates this partial trace of the Riemann tensor from the ambient space in the direction EM. Okay, so now we're gonna forget about this until the end of the talk, but okay. So now let me tell you something that you're more familiar with, most of you, which is about optimal transportation. And primarily, I use this slide to fix notation. I'm going to, instead of minimizing the costs, it's depressing to always be minimizing costs. I would rather maximize the benefit. The benefit is the negative of the cost. And I'm going to look at a benefit function defined on a product of two Euclidean domains in Rn, bounded domains. You could think of those as oriented manifolds, but let's just take the orientation from being subsets of Rn. And I'm given a distribution of supply and a distribution of demand, and I'm going to think of them as being n-dimensional forms because I have to worry about orientation a little bit. But more or less, you could think of these as being probability measures. And here they are in coordinates. So they're given by densities rho and rho bar. And Monge asks us, can we find a mapping from domain omega to omega bar that pushes forward the first form to the second form that maximizes the benefit? And Kantorovich tells us, well, an equivalent problem is to minimize the integral of u against the first form plus u bar against the second form, where u and u bar satisfy this, what do you call it? Stability criterion. The sum of u and u bar dominates the benefit. And let me also point out that when f happens to be a diffeomorphism, then this constraint can also be written in the form of a prescribed Jacobian that says the determinant of the derivative of f is the ratio of the density of rho. This is sort of becomes the Monge-Ampere equation in the quadratic case. Okay. Everyone's happy with this slide? Great. So now let me remind you what Matringer and Wang were able to show about this situation. So they show, let's take the benefit function to be 4 times continuously differentiable up to the boundary. And then for every fixed point in the source domain, I want the mapping from the target domain to the x derivative of b to be invertible. And I even want it to be a diffeomorphism. But once it's invertible, what guarantees that it's a diffeomorphism is basically that the determinant of the mixed partials of b with respect to xi and x bar j should be non-zero. And I'm just going to assume that's otherwise I reverse one of the coordinates in the bar domain. I can make this positive without loss of generality. And so this is buried in my first assumption, the way I've written the first assumption, which is not quite how Truding and Wang wrote it, but anyways. And then the other thing that you want is that the image of this diffeomorphism for each x should be a convex set. And by the way, in the case, so the case that Yan studied was bxy is the inner product, or bx x bar is the inner product of x with x bar. Then this diffeomorphism is actually an identity map, and it doesn't even depend on x. But in general, it might. And so then this A2 is just asking for the target domain to be convex. And actually, I've written the conditions here in a way that's a little bit it's asymmetrical in the target and source, but in fact, I want to symmetrize it. So I'm going to assume both B and its reflection, interchanging target and source, satisfy these conditions. And then there's this crucial condition A3, which is that you want every line segment in this image. So if I fix an X and look at a line segment in this image, the pre-image of that line segment under the inverse of this map will be called a B segment with respect to X. So in other words, it satisfies this thing vanishes. And if I was doing this benefit function, it would just be an ordinary line segment. But if I was doing this benefit function, then by the time I take 4 derivatives, I would have 0. So this criterion is not satisfied by this benefit function, but it is satisfied by some slight perturbations of this guy, and it's violated by other ones. And what does the criterion say? It says, whenever you have a B segment and any smooth curve in the source, if the mixed partial at 0 of this thing vanishes, then the second mixed partial should have a sign. And so this is sometimes called the Ma, Truding, and Wang criterion. And it's here I'm asking for a strictly positive. So later, Truding and Wang said, what if you only have equality here? And that would handle this case, but it's a little more subtle. Questions? So you saw these yesterday in the talk of Flavian. Yes, Gara. I would say the A3 is the obscure one, but we know A2 because before Ma, Truding, and Wang did this work in 2005, about 10 to 15 years earlier, people actually were able to prove regularity theorems for this particular choice of cost. And in 2 dimensions, it was Delanoë, and then in higher dimensions with Caffarelli and Urbas. But one of the things they realized is that the target better be convex, because if the target is disconnected, your map's going to have discontinuities in it. And so this is the generalization of convexity of the target to an arbitrary cost. Okay. And so what Ma, Truding, and Wang, and okay, so people handled this cost. Also in the 90s, people were able to handle a few other costs, like maybe this one here. With the correct sign, and I never remember what the correct sign is. This was the so-called reflector antenna problem. Or maybe the question is, what's the correct sign outside? I never remember that either. So one of them satisfies the A3 and the other one violates it. Okay, but this somehow, when Villani wrote his first book in 2003, he said, without a doubt, the big open problem in this area is to prove a regularity result for general costs, and this was the first regularity result that held for an open class of costs. And it was subsequently improved by many authors, including Truding and Wang themselves. So this is an interior regularity result. It doesn't tell us anything about the behavior of F at the boundary of the domains. They were able later to prove a boundary regularity result under a slightly stronger convexity hypothesis, but under a slightly weaker assumption on the cost that covered this one here. In Lopere, for example, oh gosh, this should have been A3. Lopere showed that if A3 is violated in the strong sense of not only being, if the thing that you wanted to be positive was actually negative, then you could find smooth bounded densities for which the optimal map was actually discontinuous. So in some sense, A3 is close to being necessary and sufficient for regularity. And so now the next thing I want to do is sort of remind you that this whole discussion has a kind of geometrical interpretation, which I discovered with Kim about 2010 or so, or at least it was published in 2010. So if I think about the Kantorovich optimizer for this problem, let me introduce this quantity that I call the cross difference. We saw this in Garo's talk this morning. You know, if you take a mine and a factory and a second mine and a second factory, the benefit of pairing them together, if they're to be optimal, had better dominate what would happen if I paired the same pair of mines with the opposite pair of factories. And so the conclusion is that this function of 4 variables should be non-negative on the product of the support of the optimizer with itself, which is going to be the product of the 2 submanifolds in the 4n-dimensional product space. Often what I want to do is fix one factory mine pair and let the other one vary. So let me when I want to do that, I'll just put the 0 downstairs. And then I want to Taylor expand this guy in x and x bar around the fixed point x naught, x bar naught. And what I get when I do this Taylor expansion is, because of the minus signs here, I'm expanding around a critical point. So the 0th and first order terms are going to vanish. And in fact, condition A1 that we know is the twist condition is actually equivalent to saying that the only critical point of this guy here should be this fellow. And so what appears in the Taylor expansion is a second order term and higher order terms. But the second order term has a special structure. And again, because of this minus sign, if I take 2 derivatives with respect to x and then set x equals x naught, the contribution from here and x bar equals x naught bar, the contribution from here is going to cancel the one from here. And there's no contributions from these 2 terms. And so in this Hessian term, you never get products of changes in x with changes in x, only products of changes in x with changes in x bar. And then you get these lower order terms. And so when I want to geometrize this picture, sigma is going to be the graph of the optimal map. And it's going to sit in the product domain of omega cross omega bar. And the pseudometric, one of the pseudo-Riemannian metric tensors that I'm going to want to take is this Hessian here. So let me call that h hat. And because that's a metric on the big space, the hat space. And it's pseudo-Riemannian because we assumed this determinant was non-vanishing. And you can also see from this, if I take some perturbation delta x and delta x bar, and if this term is positive, then when I take the perturbation delta x minus delta x bar, I'm going to flip the sign on this. And that tells me that this pseudo-Riemannian metric has as many time-like as space-like directions. They come in pairs, plus and minus pairs. And so my conclusion is, from this first observation, if I now think of x and x bar, if I take any, so the thing to focus on is plus minus here. When I keep the sign of the first perturbation and change the sign of the second perturbation, I change the sign of this sum. So somehow, for every curve here that has positive signature with positive tangent vector, space-like tangent vector, there's another curve that goes out of the thing that has negative, the corresponding curve. Yeah. Okay. And right, if I think of the x and x bar as lying on an arbitrary curve near x naught, x bar naught, and then take a limit, I get that the inner product of the tangent vector with itself with respect to the metric h hat that I wanted to put on m hat, which was the product of the 2 domains, is going to be at least non-negative. So I haven't quite proven that I haven't proven that it's strictly positive yet. If it was strictly positive, I would have a space-like surface. What I've shown so far is that it's not negative, and so I have a non-time-like surface. The graph of the optimal map by this 2 monotonicity argument is a non-time-like surface of this. And that already tells you that it's rectifiable of dimension n. So that already tells you that your optimizer is sitting on a because there are only there are n time-like directions and space-like directions in this. It tells you your graph of your optimal map never explores the time-like directions. So it's like the argument in 2 dimensions is if you have a monotone map from one variable to another and you turn it by 45 degrees, it's 1 Lipschitz. So it's already a rectifiability result. So pretty nice. It tells us that this guy here is differentiable almost everywhere. And all the hard work is to improve almost everywhere to everywhere. And moreover, to say not only is it differentiable as a submanifold, but it's differentiable as a graph over the base space. Okay. And I think I had some typos on this slide, like I flipped notation and I wrote y instead of x bar on this slide. But more or less for this quadratic benefit function, the pseudometric that I'm talking about is kind of the canonical one on Rn plus n. And for some more general benefit function, I would have a pseudometric tensor that looks like this. Notice that the metric tensor I'm talking about, so far it depends only on the choice of benefit function. It doesn't see the initial and final density that I'm trying to transport. And let me mention that this condition A2 that Garo asked about, the convexity of the target space. So because of these block zero matrices that we discussed earlier, like if I pick any x bar and look at the product of x bar with omega, that's going to be an n-dimensional null fiber in this 2 n-dimensional product space. And similarly, any x cross omega bar is going to be a null fiber in the sense that any tangent vector, any vertical or horizontal tangent vector has 0 inner product with itself for this metric. So the light cone here is not like this, it's like that, if you could call it a light cone. And the convexity that we talked about is actually geodesic convexity of these null hypersurfaces. So in other words, if I pick a point in a direction on here and I start to exponentiate it with respect to this metric, I stay on this vertical thing, and same thing on the horizontal guy. And okay, fair enough. So it turns out that having a metric which only depends on the cost function but not on the initial and final density is not good enough for what we want to do. Okay. However, it is good enough for so this was the initial observation I made with Kim in this direction, one of them. Under hypothesis A0 to A2, A3 is equivalent to a sign condition on the Riemann curvature tensor of this metric H. And it's that the Riemann curvature be positive whenever I have a horizontal vector and a vertical vector that are H orthogonal to each other. Then the 2 plane they span should have positive Riemann curvature tensor. Okay, so what's more interesting was the next observation that we made together with Michael Warren, which was let me now, I want to leave the metric H behind, and I want to multiply it by a conformal factor which takes into account the initial and final densities. And I choose this conformal factor. It's just a function that I multiply this old metric by. There's always a function that I can choose such that the volume form of the new metric is the product of the initial and final measure, or the product of the initial and final form. So that determines the conformal factor uniquely. And the virtue of making this conformal change of metric is that the graph of the optimal map is now G hat volume maximizing with respect to, say, compactly supported perturbations. So in other words, zero mean curvature. So we're back in the context of the second slide where we had no singularities, at least in codimension 1. Although in the second slide, you remember that there was this potential delicacy that you had to control the Lipschitz constant because you didn't want your tangent plane to be tangent to the light cone. And you still have that problem. That's the basic problem here, is you want to show that this graph of this optimal map is not tangent to a vertical or a horizontal fiber. And it turns out it's enough to do one. If it's not tangent to the horizontal fibers, it's not tangent to the vertical fibers either because of symmetry. Okay. And but it's already pretty interesting. Why should this graph of this optimal map have zero mean curvature with respect to this funny metric? And the answer is a calibration argument of the flavor that was introduced by Harvey and Lawson 40 years ago. But of course, you have to adopt the whole calibration machinery to the pseudo-Riemannian background, which is sort of what Mealy did, at least in some context. And so the proof sketch is that I'm going to show you exactly what the calibration is that does the job, and here it is. And all of these arguments have a similar flavor, but the way to picture it is, the way that I picture it anyways, is just think about one-dimensional fibers in R3. So for example, I have this fiber here, it's oriented, and if I want to say it's minimal length or something, well, okay, I want to say this fiber has minimal length, and I want to compare it to some deformation that might look like this. And they both, the constraint is that if I reverse the orientation on this, they bound a disk or something. And then the idea is I want to find a one form that I can integrate around this cycle. And I know that if it's a closed one form, then the integral of its derivative on this disk has to vanish. So that means the integral of the one form on this part of the cycle exactly balances the integral of the one form on that part of the cycle. And that's more or less what's going on, except here the forms are n-dimensional. And so the integral of this form over sigma is the integral of the same form over sigma prime, provided that sigma and sigma prime bound an n+1 dimensional region. And this funny metric has been cooked up so that when you try to measure the magnitude of this form with respect to this metric, it turns out to have magnitude 1. And so you get this chain of inequalities. And moreover, it's also cooked up, or rather the metric is cooked up, so that these inequalities become equalities in the case that sigma prime is the graph of an optimal map. And so that says that the volume of the graph of the optimal map is equal to 1 and dominates the volume of any other guy. And this inequality looks backwards to you because we made this convention that we were going to maximize instead of minimizing when we moved from Riemannian background to pseudo-Riemannian background. So this is like Cauchy-Schwarz or something, but it looks like it has the wrong sign. But it doesn't because we're, Okay, questions? Okay, so that was the story with Micah Warren. I haven't left as much time as I might like, but okay, never mind. So here's the final theorem I'm going to discuss. But in order for this theorem to make sense, I need to first fix a metric on the source domain, let's say the Euclidean metric. And then I want to induce a corresponding metric on the target domain, or on the product of the two domains, and here it is. And again, I put the same conformal factor in front of it so that the volume of this is now a positive signature metric, a Riemannian metric. So the volume form of this Riemannian metric is the same as the volume form of the pseudo-Riemannian metric, G hat. And notice that the hypotheses now yield a positive number such that the Riemann tensor that I said was positive before is going to be bigger than kappa times the area spanned by one of these, a pair of horizontal and vertical vectors, P and P prime. And now the theorem, so first of all, we can't say anything at the boundary. We're only going to do an interior regularity result. So we need to choose a compactly supported cutoff function, smooth. And this is going to be an a priori estimate, because the way the Trudinger-Ma-Wang argument goes is they say, once you've shown that this thing is bounded away from the horizontal or the vertical, then this thing is actually, it's a Lipschitz graph. And once you have its Lipschitz as a graph, you can apply Evans-Krylov and see that it's C1 alpha, and then you're in the world of Schauder estimates, and so higher regularity. Then you're dealing with a scalar elliptic equation, and higher regularity is straightforward. Okay, so all we need to do is give an a priori estimate that quantifies the spake-likeness of this graph, how far it is from these null horizontal and vertical fibers. And here's the estimate. The restriction of the signed metric to our submanifold is bounded away from 0 by the Riemannian metric, by the restriction of the Riemannian metric, times some factor that depends on the cutoff function and this number here. And of course, what's crucial again is that we don't want this little constant here, or it's a big constant, but we don't want this big constant to depend on the data or the submanifold or whatever. And so what does the constant depend on? It depends on the G hat and the S hat and the cutoff function. And it depends only on the L infinity norm of the log of, say, both densities. In fact, one density is enough because of the normalization that we baked into S hat, or K if you like. But otherwise, apart from this, it's independent of the initial and final density. That's the issue. And so I'm going to try to show you a proof. And the proof goes in 2 stages, or 2 slides at least. Are there questions about the statement? So the first slide is going to be familiar to some of you, and the second slide perhaps not. So the first slide is, you look at the condition for the optimal map. It has to produce equality in this inequality. And so you get a first and second order condition, which many of you have seen. And if you differentiate, we're dealing with smooth maps because, Matri and Wang showed that if you can show this a priori estimate that doesn't depend on this stuff for smooth maps, then you can figure out that even the non-smooth maps enjoy it as well. And so you differentiate this guy, assuming F is smooth, and you get this second order relation. And now you take the determinant of this. And the point is, the left-hand side this is somehow, I'm going to use the Monge-Ampere equation, or the analog, the prescribed Jacobian, to take care of this derivative of F. So here it is. It's the ratio of the initial and final density rho and rho bar. And this is something that's bounded away from 0 by our hypothesis. So the right-hand side is bounded by hypothesis. And that tells us the left-hand side is bounded. And that tells us that we can improve this non-negativity to strict positivity. So that's already something. But what we really want is we want this to be the strict positivity uniform. We want a bound that doesn't depend on the data that keeps this thing away from 0. But notice anyhow that this is a second order fully nonlinear equation for U that determines how do I find U in terms of the data rho and rho bar. Okay. And so then the slide that's perhaps less familiar is this final slide where we show how do we improve strict positivity to uniform positivity. And here it is. So we fix the point which maximizes the largest eigenvalue of the Riemannian form times the cutoff relative to the restriction of the pseudo-Riemannian form, which is also Riemannian, which also has Riemannian restriction. And so we can extend our Euclidean coordinate system. You choose a rotation that diagonalizes the thing that appeared under the determinant. And you can then extend that coordinate system to a set of Riemannian normal coordinates for S hat. And we want to take Pi to be the eigenvector of this matrix, which has eigenvalue lambda I. And then we can build. So I've taken the PIs down here, and I can figure out how to construct a guy here so that I'm tangent to the submanifold. And I use the Jacobian derivative of F to do that. So the relation between the Pi and the Pi bar is given by the Jacobian of F. So that when I add P and lambda, sorry, this should be a Pi. When I add Pi to lambda I Pi bar, I get something in the tangent space. And when I multiply it by this factor of negative square root of lambda, I get something that's normalized in the tangent space. And this gives me an orthonormal basis for the tangent space. And moreover, it's simultaneously, this is an orthonormal basis with respect to G, but it simultaneously diagonalizes S. And except S is not normalized, rather the size of S, which is the thing we want to bound away from 0, or away from 0 and infinity, is measured by mu, which is the sum of lambda I and its reciprocal. So this is clearly bigger than 1, but the issue is we want to show this is bounded away from infinity. So let me order the eigenvalues so that un is the largest one. And then I exploit the multilinearity of the Riemann tensor and the special structure that comes from the special structure of my metric. And I get that when I look at the Riemann curvatures of interest, they're bounded below by kappa times this ratio of eigenvalues, minus some things that are not too harmful. And now you sum this bound to get the partial trace of the Riemann tensor that we saw earlier. And there are only n minus 1 terms in this sum, because if I put en here, I would get 0. And so I have a sum of these ratios, but I use the relation between the arithmetic and the geometric mean and the fact that the product of all the eigenvalues, the determinant is bounded, to get this slightly nonlinear, the slightly larger than 1 power of the largest eigenvalue mu n. minus a bunch of other things that are controlled because mu n is the largest eigenvalue. And if you remember our previous lemma and corollary, we also had an upper bound for this in the term of the form constant times mu n, where these constants don't depend on the harmful data. And now I have something larger than 1 dominated by constant times something linear, so that says the mu n is bounded. So that's the a priori estimate. And then the rest is standard. So, all right. Thank you very much.
Thank you very much, Robert. Do we have questions?
So yeah, wow. So at the end, Robert, I mean, it's super clever, but I didn't understand how this Mark-Trudinger-Wang condition entered in the estimate at the end.
Well, okay, so okay, so let me. I am not sure that I can. I would have to think about where. I mean, yeah. So we have the sum, and we saw the earlier estimate this sum, and I don't remember which. I mean, okay. So let me go back to the beginning. So. Yeah, I don't, to be honest, I would have to think about where it comes into the proof, but whether it's in this initial lemma or the final lemma that we use it.
So because it means it should have an interpretation as some curvature sort of bound.
Okay, yeah. So yeah, if kappa has the wrong sign, then I won't be able to control this ratio by this using the I'm trying to apply the arithmetic geometric mean inequality. If kappa has the wrong sign, I won't be able to do it. The inequality will go backwards. To relate, I want to get rid of all these lambda i's by relating them to the determinant, which I can control, provided I put in the lambda, the last guy. And that's what gives me this extra little juice here. Thanks, Garo.
Oh, there's.
Yeah, sorry for being in the theory of regularity for optimal transport, there was a special case of Riemannian manifold when the cost is the
distance squared.
And so how does it? How can you consider this special situation in your framework now?
Right. Okay. So, I mean, Lopere has your former student Gregoire Lopere. So, if I take, for example, my underlying space omega to have a Riemannian metric S on it, and I define the associated distance, and I use that or maybe minus that as my cost. Maybe some function of the distance, little f, let's say. Typically f is square, so or minus the square. So if this is my d, then there's something preferred. If I want to deal with this kind of cost here, then omega bar better be omega, because distances are defined on product with the space with itself and not somewhere else. And then when I look at the product with omega and omega bar, the diagonal plays a special role. And if I look at the Riemann curvature tensor of this thing h hat that I introduced, on the diagonal, it will coincide with the Riemann curvature of this underlying metric S up to some constant multiple, which I think is 3 or 1/3. Off the diagonal, it now involves pairs of points on the underlying manifold. And so it corresponds to something like the integral of some derivative of the Riemann curvature along a curve that joins those 2 points, along maybe a geodesic joining those 2 points. That's probably the best I can do.
All right, I think it's time to move on with the next talk. So let's thank Robert once again. Okay, we can start with the last talk of this morning. It's my pleasure to introduce Chloe Jimenez from the University of Brest, and she's going to speak about bridges between several notions of viscosity solutions in the Varsity space.
Okay,
Please.
thank you very much. Thank you to the organizers for this invitation. I'm really, really happy to be here. It's a great pleasure. Okay, so I'm going to talk about several notions of viscosity solution in the Wasserstein space, 3 of them actually, and I'm going to try to make them be natural and to make bridges between them. Let me start with the L2P representation of the Wasserstein space. I'll try to go slow so that if anyone is not familiar, he will catch it. I will need a reference probability space. So if you want, you can think of just the interval 0,1 with its Borel tribe and the Lebesgue measure on the 0,1. But you can take a more general space. Here, omega has to be a Polish space, metric, separable, and complete, and a P with no atom. So as everyone knows here, for any mu in the space, in the Wasserstein space, I can find a transport map from omega to RD, which is in L2, such that X transports P to mu. Or, in other words, I can find a random variable such that the law of this random variable is mu. Okay, so for any mu, I have, in fact, many, well, only one if it's a Dirac mass, but in general, it is a class of representative in L2P. So if I want to do some transport, I need also transport plans. So if I take a transport plan, I will represent by 2 random variables, x and y, in L2P from omega to RD, such that my transport plan is the law of the couple. And of course, you ask that x should have law mu, and y should have law nu. So each plan is represented by, again, a class of couples of random variable. Let me do a very simple computation just to make us at ease. If you want to compute the cost of the displacement associated to gamma, so here your gamma is the law of some xy. So you can put the xy inside your integral, and you get an integral on gamma. With respect to p, and with the power 1/2. So you get, in fact, the norm, the L2P norm of x minus y. And you can do this for all xy that represents your gamma. So you have this equality. The Wasserstein distance is the minimum of an L2P norm for all x and y, such that x has low mu and y has low nu. And okay, so now if we look at the topologies, the easy part is to, if we have a sequence xn converging to x in L2P, well, of course, you can look at the plan x and x, which will be a gamma n. And so you will see that the Wasserstein distance, which is less than this quantity, will converge to 0. The opposite implication is less obvious. If you have the Wasserstein distance between mu n and mu, which tends to 0, you can find a good sequence xn and a good x, for which x represents mu, xn represents mu n, and you have the convergence of xn to x. So the L2P topology and the Wasserstein topology are the same in the Wasserstein space. And now if we look at maps from P2 to R, we can also represent them as maps from L to P to R. Just by using this trick, the capital U is the lift of a small u, and to each x, you take the law of x, and you take small u of the law. So when you do that, you don't get just any map from L to P to R. You get a map that has a property to be rearrangement invariant. That means that if x and y has the same law, capital U of x will be the same as capital U of y. It depends only on the law of the random variable. And from what we have seen before, the continuity of small u is the same as the continuity of capital U. So it goes perfectly. Now with this setting, I'm going to explain what is the Lyon's derivative. So the definition is quite simple. U is differentiable at some u0 if and only if capital U is differentiable at some x of low mu0. So it's nice because we know how to differentiate in L2P, but just like this, well, some questions arises because, of course, here is an x which represents mu0. What happens if I take another x, x prime, let's say, which represents also mu0, and what is the shape of the gradient? Well, in fact, Lyon's gradients can be seen as plans, let's say transport plans, if you like. In fact, if we take a pair x prime, z primes, who has the same law of x du of x, then z prime is equal to du of x prime. So let me write this because it will be useful. Yes, yes, well, right, thank you. So, okay, so now the x has law mu0. And I'm going to see x du of x as a plan. And what happens is that if x prime, z prime is also of law gamma 0, then z prime is equal to du of x prime. So keep that in mind. So what does that mean? It means if I choose 3 random variables, x prime, y, and z prime, such that x prime, z prime has the same law of x du of x, I have this equality. So now let's look at it as, let's say, transport people, and see here you have a triplan, x prime, y, z prime, and the only thing you ask to this triplan is to have the marginal in, let's say, x and z, in the first variable and the last variable, equal to my gamma 0. So let me write this. So here you can take every one you like. This u of x is actually u of x of mu0. This one is u of y p. And here, so I have z prime y minus x prime, and there is a rest. For the moment, I don't look at it. So if I say, okay, this guy is in fact a triplan, which I denote with a LaTeX letter of varpi, I don't know the name. And so this is an integral of z. Here you have a displacement, and you have here varpi x, y, z plus o. And this will be true for any varpi which satisfies that the x, Z marginal is gamma 0. So this gives you an equivalent definition of the derivability, of the differentiability. U is differentiable at mu 0 if, when I set here gamma 0, the law of this couple, for any nu, this is the law of y, which be any one you like, any triplan with the x z marginal equal to gamma 0 and the y marginal equals to nu, you have this equality. And this is reminiscent of a subdifferential appearing in the book of Ambrosio, Gili, and Savary. So this means that gamma 0 is in the subdifferential of Ambrosio, Gili, and Savary, and also the opposite plan. So to make a differentiation in L2 is the same thing as doing this trick with triplans. Well, but we can go a little bit deeper. These not only gradients are plans, they are plans supported on graphs. So let me show you that. You will see it by taking a particular triplans. So here, so you choose the new, everyone you like here. And okay, let me erase. Oops. I need some space. So you want to move from mu 0 to nu. So you choose any nu you like, any plan you like. Mu 0 nu, excuse me. And you choose a triplan. The triplan must have a marginal in x, z, gamma 0, and in x, y, gamma nu. So what I do is I glue the maps together. So I disintegrate gamma 0, and I put gamma nu here. So now, if I look at my the integral in the middle, let's come back maybe. Let's write this integral. This is like this, and I have gamma 0. Let's write it gamma 0 x like this. I have disintegrated gamma 0 and gamma nu, and here there is the z. Well, this letter appears only here and here. So I put the integral inside. And I get this. Where here, this is the barycenter of my gamma 0. Okay, so this is the computation. And so if I rewrite, this is true for any nu and any gamma nu. So when you write it in L2, it is true for any choice of x that represents mu 0 and any choice of y that represents its nu. So you get this. And this says that the gradient of u is this guy. Yeah. So this is the way here you are on a plan which is supported on a graph. And this gives you the representation theorem, which was first shown by Lyons in the C1 case, and after by Gambo and Tudorescu in the general case, and which say that U is differentiable at mu 0 in the sense of Lyons if it exists some P in L2 mu 0, it's a plan if you like, such that du of x, a map, not a plan, du of x is P composed with x, and for all x of Lyon mu 0. And moreover, Gambo and Tudorescu showed that P is in the tangent space to the Wasserstein space which I write for in purpose because I will need it. There are several definitions, but I write it as the closure in L2 mu 0 of the gradient of a regular phi. Okay? So this is the way to differentiate billions, let's say. So if we come back to this definition in the space of Wasserstein with forgetting about L2P, so this is a definition by Garbo and Tudoracu. Now, U is differentiable at mu 0 if it exists some P in the tangent space such that, okay, so you do the variation. So you choose your destination, you start from mu 0, you choose the nu where you want to go, and you choose the way to go from mu 0 to nu by choosing a plan, any plan. And here you have the integral with this P, which is the gradient, and the displacement. Of course, you could ask why take all the plan between mu 0 and nu, why not restrict to all the optimal plan? Well, it happens that it doesn't change anything. So you can, if you want, restrict your gamma nu to the optimal one. And I will denote this P by this gradient here. Okay? Examples. I will need 2 examples here. The one is called monomial by Lyons, which is the map which has, maybe I can use the pointer if I understand how does it work. No? Okay, never mind. So at mu, you associate the integral of phi d mu for any mu, and phi is fixed. Then the gradient of u is the gradient of phi. So you differentiate inside. And the other interesting example. Oh, okay, thank you. Thank you very much. So the other example is the square distance. So you fix your nu, and you look at the square Wasserstein distance. Well, unfortunately, this is not differentiable everywhere. It is differentiable only if the optimal plan between mu 0 and nu is unique and supported on a graph of a map T. Then the gradient is 2 times identity minus T. And this appears again in the book of Ambrosio, Gilles, and Savary. And they did this computation before the appearance of the gradient flows, if I don't mistake. Okay, so let me move to viscosity solutions. What type of equation I'm looking at? Well, I will look at backward Hamilton-Jacobi equation, but you could rewrite it forward if you like. And there will be 2 variables. One is a time variable, which will be in an interval 0t, and the second one will be a probability measure. And you will have the time derivative plus an Hamiltonian, which takes as argument mu, and here d mu. It will be defined, this Hamiltonian, for any mu p in p2 times L2. Okay, we could reduce to the tangent space, just take L2. And here there will be a final condition. So let me look at this equation in what happens usually in Rn, just to give an idea. So in Rn, you will have du of Tx plus the Hamiltonian in x dx u of Tx equals 0. And usually what happens if your solution is not regular, you cannot differentiate it. So you replace this part and this part by an element of the Fréchet subdifferential or superdifferential. Okay. So the idea will be the same in P2. And from what we have said before, there are two different types of Fréchet subdifferential that appears. Well, forget for the moment of the time variable. One of them comes directly from the Gambo to the Rask definition of differentiability. So in the subdifferential, we will have elements of the tangent space. And again, when you choose to move from mu0 to nu, you choose also a plan, and you have well, it's the same definition as before. And the other one is to come back to L2 and say, okay, I will use the L2 subdifferential and or equivalently, Ambrosio-Gilli-Serraj subdifferential. Well, here, the idea is, as I said before, you can see this type of element as plans supported on graph, and here we have plans. So it will be a bit more general. So this point of view is the one of Gambo and Guillen to Rascu, and I'm going to speak about it first, and I hope I will have time to speak also about the second point of view. Actually, I will have two notions coming from this Fréchet subdifferential, the Gambo and Guillen to the Rascu one, and the second one will be strict viscosity solution, which was introduced by Marigonda and Quincampoix. So, well, the definition is what you expect. So now you have two variables, time and Wasserstein, let's say. So t mu0 in 0t time p2. And an element of the subdifferential is such that the mu part is in the tangent space, and you have this inequality. So now you have this time element, which is the same as it will be in R. There is no surprise in it. And you get again this scalar product. And U is a viscosity solution of the Hamilton-Jacobi equation if for all T0 mu0 and all elements in the subdifferential, we have this inequality. So you replace the differential part by the element of the subdifferential. And you define subsolution in the same way. And you, well, you have reverse inequality for subsolution. And you take here the Fréchet superdifferential with the inequality reversed. Okay, so there are several questions. In Rn, you can define also solution using test functions. So is it possible to do it here? Yes, but to do that, you need a different notion, which is strict viscosity solution. And we will see in a moment that these notions are equivalent under assumptions. So let me move to approximate subdifferential. To define strict viscosity solution, I need this notion. So now there will be an epsilon here, which is strictly positive. My subdifferential depends on that epsilon. It contains, again, elements of the tangent space. And when I move from mu0 to nu and from t to nu, again, I choose a transport plan. And OK, everything is the same as before, except that now I have this term here, which is not exactly something I can put here in the small o, but it tends to 0 when t tends to t0 and nu tends to mu. Okay, so how do Marigonda and Quincampoix define a solution? They say U is a strict viscosity solution of HG if it exists some constant, which is fixed, and such that for all epsilon and all T0 mu0 and all elements in the approximated subdifferential, you have the inequality, but with a C epsilon there. And if you want strict subsolution, you reverse the inequality, but you put a minus here and a plus here. an important thing, maybe I just come back a little bit. If you take an element of the Fréchet subdifferential, not the approximate one, it will be inside the approximate Fréchet subdifferential for all epsilon, because you will have this inequality. Well, I'm doing a reverse thing, I think. It's the opposite. Okay, no, never mind. Okay, no, so the thing I wanted to say, but I'm just mixing my idea, is that the notion of a strict viscosity solution is stronger than the notion of solution. And well, for both notions, there are comparison theorems, but with different assumptions. They both appear in the context of control theory. And well, some equations were studied with one definition and the other with other definition. So can we put all these things together? So we will see it. But before and okay, there are two questions. One question is the question of test function. Can I express this with test function? And the second question is whether these notions are equivalent. And in fact, to prove the equivalence, I need some test function which are regular in some sense. So let me show you. So it is possible it is possible to express the notion of strict viscosity solution with epsilon test function. And this comes from the fact that elements of the subdifferential are inside the tangent space, and they can be approximated by gradient of var phi, which are regular, and these var phi's are the gradients of functions which are like this, monomial. And here you can play this game of approximation because you have the epsilon. It helps you. You cannot do that if you move to a viscosity solution. You can just do that with strict viscosity solution because of the epsilon. Well, the definition of test function I'm going to introduce is very similar to the one introduced by Crandall and Lyons in the context of viscosity solution in infinite dimension. So let me start with this. So your test function well, it will be an epsilon subtest function at u at t0 mu0. So like in Rn, it will be equal to u at the point you are considering at t0 mu0. And well, usually you don't have this blue term here. You have that u is greater than v in the neighborhood of t0 mu0. Here it's not exactly greater, it's almost greater. You have this term in blue, which plays a role. And well, the regularity is not so good. At the beginning, what we had is that V is continuous everywhere and differentiable only at t0 mu0. But I'm going to show you that I can have a little bit more regularity, and this regularity, this extra regularity will be enough. So let me show you the shape of the test function. So remember, you start from a PT P mu0, P mu, and you want to approximate. So PT, it's okay, it's good, it is in R, so it's a gradient. And this one, you want to approximate it by some gradient of phi, which are regular. So in my test function, I will have this phi. Ouais. Oops, non, c'est pas ça que je voulais faire. Phi here, your PT appears here, and you have, well, here you have a term which represents the small o. It's the same, actually the same construction that you will do in Rn, so you will have this term. Okay, excuse me. And this psi is supposed to be regular, and it satisfies psi of 0 is equal to 0. and psi prime of 0 is equal to 0. So that if you take here t nu equals to t0 mu 0, these elements disappear, this one also, and psi also. So you have this, the equality. V touches u at t0 mu 0. What happens if you differentiate it? Well, you will get here in time pt, and here gradient of phi, and this term here will disappear also at t0 mu 0 because you have that c prime of 0 is equal to 0. So this is in t0 mu 0. Now, if you move from t0 mu 0, you get into trouble because of the Wasserstein distance, which is not differentiable everywhere. Nevertheless, it is super differentiable everywhere. So that, because I choose here psi to be non-increasing, we have that the subdifferential of my test function is non-empty everywhere around t0 mu 0. So I cannot differentiate it, but I have elements of the subdifferential. And moreover, there is some regularity. If Tn tends to T0 mu 0, I can find a sequence on the subdifferential with the convergence Tn tends to T0 and mu n tends, and excuse me, you have the conversions Ptn tends to the I am lost, excuse me. Okay, let me write it on the blackboard, it will be better. So, okay, so you have your function is you have this exists, okay? This exists, there is no problem with that. And you have also the derivative in time, it exists also. So now if I take Tn that tends to T0 and the mu n which tends to mu, I can find an element Ptn, P mu n in the subdifferential. Such that, okay, my Ptn will converge to the, here, this part. And also we will have the P mu n that converges to the gradient at mu. In which sense? Well, in the sense that you see this element as a transport plan, as a plan transported on a graph, supported on a graph. And again, this element, you see it in the same way. And here you put the Wasserstein distance. So this will be enough. First of all, it is equivalent to look at strict viscosity solution in terms of subdifferential or in terms of a test function. And moreover, if your H is regular for this topology, I mean looking at element of L de mu as if there were transport maps, then, and of course, here you need also this condition, which is nice, but not so nice. In fact, you have the Lipschitzianity with respect to the second variable where mu is fixed. Then U is a strict viscosity solution if and only if it is a viscosity solution. You can you can make this condition be weaker by saying it should be locally Lipschitz. Okay. So let me give an example. This example was studied by Marigonda and Quincampoix. So it comes from optimal control. It's a meilleur problem. So you want to minimize a final cost on all curves in the space of Wasserstein that are absolutely continuous. You fix that the starting point is mu 0. And you control the dynamic, the VT, which is appearing in the continuity equation should satisfy a dynamic. And here you choose the control in the better way to minimize this thing. So they show that V is the unique strict viscosity solution of this equation with this Hamiltonian, which is in fact similar as the Hamiltonian you have in RN when you study the mere problem. It's just that now you integrate with respect to mu. And well, so they show it is a strict viscosity solution and it is unique, the unique strict viscosity solution. And now we can say it's also the unique viscosity solution. Okay, so yes, that's nice. So let me end with Lyon's notions of viscosity solution. So in his lecture at the Collège de France, he proposed the following idea. Just take the lift of the Hamiltonian in the following sense. If we have here the law of X and P, again, we can see it as a plan supported on a map and write it, well, for me, it's a plan supported on a map. He didn't say that. And just write a capital H of X, P composed with X is equal to that. And now if you want to do a Hamilton-Jacobian equation in all L2, you have to extend, because here you have to be able to put some Y, which is not written in this way. So you extend it and you use the notion of a viscosity solution in L2. He considered this example where here there is the square norm, so that the Hamiltonian is just the square norm. And he say, okay, I take a natural extension, which is the square norm in L2. Here, the Hamiltonian is quite nice, and the Hamiltonian is again quite nice. There are several extensions that appears in the literature. I will maybe talk of them later if I have time. I will present you another one. My goal was to preserve regularity. This guy looked nice, this one also. Let me show you. So the idea is the one I'm telling you since the beginning. Just consider mu p as a transport plan supported on a map. Well, any transport plan can be approximated by a plan supported on map. Be careful here, I can move both marginal at the same time. So I don't care if mu is absolutely continuous or so on. If H is regular, we extend it from transport maps to transport plans. And we will get, we take the lift of the Hamiltonian just by saying that H of the pair is H of the law of the pair. So it gives you this results. So assume H is uniformly continuous. You could ask also it to be locally uniformly continuous. It would work. And just set H of a couple is equal to the limit of H mu NPN for all mu NPN satisfying this. So you see mu NPN again as a plan supporting on the graph, and you make it converge to XZ for W2. Then H is regular, and it is in fact the only regular Hamiltonian satisfying this. You get regularity in L2 because regularity in L2 is the same as the regularity with respect to Wasserstein 2. How many time do I have? Like 5 minutes? 7 minutes? Okay. So some example, if you do the construction with the Hamiltonian of Lyons, you get the extension of Lyons. You can do it also with the Marie-Gondac and Campo example. And okay, so just think of it. Here, the PX is assumed to be a transport map again. So you want to move to plans. So you make here you have x px, and here you get x z, which is inside here. So it's like you were integrating with respect to a plan. And what is nice with this extension is that remember we had the solution, the value function. If you take the lift, you can show that it is the solution of the extended equation. So it preserved this result. Okay, maybe I end with other extension existing in the literature. I know two of them. I know one by Gambo Tudorascu and one by Cavagnari, Marigonda, and Kagompo. Well, they are not regular in general. This is the default. Nevertheless, the one of Gambo and Tudorascu is really, really interesting. What does it do? Instead of extending by regularity, it makes projections. So you want to define your Hamiltonian for any xz. What do? You project your z in all the p composed with x, where p is in the tangent space with respect to the law of x. So it is a quite regular, quite natural idea. And unfortunately, it's not regular, and you can see it with the example of Lyons, because as you project, you will have something which is less than the regular extension. Nevertheless, it is beautiful because it gives you the perfect equivalence between viscosity solution in the space, the Wasserstein space, and viscosity solution in L2P. So it gives you also the meaning in L2P of what is a Gambo and Tudorascu viscosity solution. So it is important to mention it. Okay, so let me finish maybe by other elements in the literature. Just focus on this idea to define viscosity solution with plans. And there is an article by Bertucci who uses almost the Ambrosio-Gili and Savary subdifferential, but only with this particular tree plan I used before, which are made by gluing the plans. And I want also to mention a work by, I think it was introduced by Zidani, Geraoui, and Osedat. I don't know if she is here. Okay, Avril, here. And well, they use something which is also, I think, very natural. They make they use the Ambrosio-Gili and Savary, but they reduce it to elements that are in the geometric tangent space. And well, in fact, I didn't mention it, but you can prove a comparison theorem for the for an Hamilton-Jacobi equation in L2P, let's say the extending one, for instance, but just looking at rearrangement invariant solutions that are the ones which are meaningful in L2P. And when you do that, you see that the assumption, well, you can reduce your Fréchet subdifferential to this one, and it will work the same. So I think what they do is quite meaningful. And well, I will stop there. Thank you very much, and buon appetito.
Thank you very much, Chloe. Do we have questions?
Thank you for the talk. There is also the notion of metric viscosity solutions that was implemented, let's say, in the Wasserstein space. On your class of regular extensions, do you know how they compare to taking just the elements that are supported on graphs?
I think I've missed your question. Can you do it again?
Sorry. So there is the notion of metric viscosity solutions that is very general, and it has been implemented in the Wasserstein space. And what appears is that if you want to compute the metric, the metric slope of the function, you need to take also the element that split the mass. So you cannot reduce to only plans that are supported on graphs. But maybe on your extension, since it's regular, maybe there is something more. Do you know if the regularity of the Hamiltonian allows to make the link, or?
No, I didn't check that. Maybe you can do it.
Do we have further questions? Guillaume.
So maybe by curiosity, there are all these notions, and once more was mentioned in your question, but you can think also in problems. These problems may come from many particles and with symmetries, problem Hamilton-Jacobi equation in finite dimension, and then lifting, which probably is related to taking the probability space to be discrete in the beginning and to try to pass to the limit. Is there one notion of viscosity solution which somehow emerges as a quite natural limit, letting the number of particles go to infinity as viscosity solution in finite dimension plus symmetries?
It hasn't. I think it has been studied in MFG, no?
And
more
then,
or less, no. And I know you think they didn't do the computation for Hamilton-Jacobi. I don't.
yeah, but my basic question is there one notion of viscosity solution which emerges quite naturally for natural class of Hamiltonians?
Okay, I understand. Okay, so
Or
you say what
maybe it's stupid.
the one selected by passing to the limit? No, that's an interesting question. I don't know.
Other questions? Well, if not, oh, yeah.
Yeah.
I concentrated my my question for you as a chairman. Yes. So I'm curious about you may remember this paper by Ambrosio and Gangbo about Hamiltonian equation in infinite dimension, and
Yes.
I would be curious whether there has been some progress in using different kind of solution formulation as you did for Hamilton-Jacobi, or maybe it's I didn't follow the literature very closely, but have you heard about, I mean, or contributed to any progress in that direction?
Well,
so maybe you don't remember. I mean, this paper
of Ambrosio Gambo, where they studied
Hamiltonian equation in
yes.
infinite dimension.
Yes.
Which is different from Hamilton-Jacobi.
Yes. Well, yes, but well, I think the subdifferential, which was introduced later by Gambo and Gwen to the Raskuk, was emerging from your paper, I think. Yeah. Well, I'm sorry, I don't know.
All right. Before thanking Chloe and all the speakers this morning, let me remind that we are going to take the group picture in front of Palazzo Carovana, the main building of Scuola Normale. So please follow the flow of people before going to lunch. And now let's thank Chloe and all the speakers of this morning. All right, welcome back. Time to start our afternoon session. It's my pleasure to introduce Hugo Lavenan from Bocconi University, and he's going to speak about gradient flows in the geometry of synchron divergences. Please.
Thank you, Nicola, for the introduction, and thanks to the organizers for giving me this opportunity and for this very nice meeting. So today we'll present the concatenation of two projects. So the first one with Jonas Lukrach, Gilles Mordant, Bernard Schmitzer, and Luca Tamenani will more be about the geometry of synchron divergences, and is already on archive. And the second one, which is sort of a follow-up with Mathis Ardion, who is somewhere here in the room, which is for the moment a master thesis, and we are in the process of transforming it into an article, and which is about gradient flow in this geometry that we explored with Jonas and Gilles and Bernard and Luca. But first, let me start with a motivation. And the full disclaimer is that it's not the actual motivation of the project. It's not how we started it. But I think it's sort of a nice story, which is about so putting entropy in the JKO scheme. So we already had some presentation of the JKO scheme or minimizing movement scheme. So you are in the Wasserstein space, you have E, which is an energy, and what you're doing is iterating, so the proximal operator of E, so you try to minimize the energy plus the Wasserstein distance squared, the optimal transport cost with quadratic cost, say, between the previous point and your current iterate, you divide by this parameter tau, and we all know that when tau goes to 0, this converges in standard sum assumption towards the gradient flow of the gradient flow of the energy E in the OT geometry. And so what I would like to sort of do today is to explain how we can use entropic optimal transport in this context. What is a good way to use entropic optimal transport in this context? And this will give rise to a new gradient flow. And the magic trick is that this gradient flow, which actually looks like, after some change of variable and some change of geometry, like a rotation, which is quite surprising because you start with a gradient flow and then you rotate. There is not exactly the case, but I will explain. So if I tell you, okay, can we use entropic optimal transport in the JKO scheme? Maybe you say, well, it has already been done. So indeed, it has already been done. So first, let me recall the definition of entropic optimal transport. So you have a new parameter, which is epsilon, which is the noise level, and the set of constraints is the same. Here I have, say, an arbitrary cost function, and I add into my objective functional the relative entropy of the coupling with respect to the product measure. So I also want the coupling to be close to the independent coupling. Why you would do this, the original motivation is that it's easier to compute via a SYNCON algorithm. And I think that in the, say, past 10 years, just one motivation is also this as an object is interesting to study, even though, say, epsilon is not small. It's not only interesting as an approximation of optimal transport, but is interesting as an object to study in itself. So if you have the entropic OT, the standard thing to do would say, I take the JKO scheme and I replace OT by OT epsilon. And this is, for instance, what Gabriel Perret did already more than almost 10 years ago. Now, what does it do? So to understand what does it do, you would be interested into the, say, asymptotics of OT epsilon when epsilon goes to 0. So there are experts of this in the room. And so basically the ideas, I mean, if you look at the results, is that OT epsilon is, at first order, it's OT. Then you may have constant terms, but I ignore them because I'm minimizing. And then the next term in the expansion is of order epsilon. So that if then you plug it into the formula, you look at the new energy that you're minimizing is more or less the original JKO energy, plus epsilon divided by 2 tau times some bias. So at this point, it makes sense to say, well, I would like, if I want to recover the original gradient flow, I will take, I want the bias term to disappear. So I would take epsilon to be much smaller than tau. That is, as I decrease my time step, I also have to decrease my noise level. So this was proved by Carlier, Duval, Perret, and Schmitzer, that if epsilon is much smaller than tau, then you converge under some assumptions to the Wasserstein gradient flow of E. Then if you take epsilon exactly of order tau, the bias term is basically of order 1, and so you can put it into the energy. So as far as I understand, this is an ongoing work by Emric Barada, Anastasia, and Filippo, where they would say that it could converge to a new flow, but still it converges to, converge this to a new flow, but something which is well posed. Now, if epsilon becomes much larger than tau, then everything breaks down, and basically you have you don't converge to a flow when tau goes to 0. Today, I will take epsilon, which is fixed. Okay, so today, because the problem is that taking epsilon, which is smaller and smaller, for instance, from a numerical point of view, does not behave well. So today, I would like to take epsilon, which is fixed. And so, a priori, well, doing this will not work because I am in the third situation and everything breaks down. To have something which does not break down, I will introduce the SYNCON divergences that were in the titles. So the SYNCON divergences were introduced by Genevet and co-authors as a way to debias the entropic optimal transport. So the formula for the SYNCON divergence is you take the entropic optimal transport, but you subtract the self-transport term so that you subtract 1/2 of OT epsilon mu mu, 1/2 of OT epsilon nu nu. Why you do this? Because OT epsilon has the tendency to be strictly positive when the two measures are equal, which is the bad thing if you want it to behave like a distance. And so this S epsilon at least has the good taste of being equal to 0 when the two measures are equal, when you are on the diagonal of the product space of probability distributions. What is surprising, and what was proved by Fedi and co-authors, is that under an assumption that exponential minus c divided by epsilon is a positive definite universal kernel, I will go back at some point to this assumption, but if this is the quadratic cost, it works. Then S epsilon behaves more or less like a distance squared, in the sense it is always non-negative. It is equal to 0 only on the diagonal, and actually it metrizes weak convergence of measures. I am on a compact set, so there is no problem of moments. Moreover, it is still a convex function of each of its inputs, not jointly convex, but it is not a distance, so its square root is not a distance. So S epsilon is not a distance square, there is no triangle inequality. However, so it still behaves more or less like a distance square, and so it would be, it is natural to say, I take the JKO scheme, and I replace OT, not by OT epsilon, but by S epsilon, the syncon divergence, because this will give me something which behaves like a distance square. So an alternative title for this talk would have been, because I will be studying this, say, scheme in this talk, and so it would be everything you always wanted to know about the syncon JKO scheme. I don't like that much the acronym, but so okay. But why do you expect this scheme to be better posed? The point is that syncon divergence, what it behaves like a distance square, is that so they are 0 when the two measures are equal, and as we will see, they have a quadratic detachment from the diagonal. That is, if, say, you take, for instance, a smooth curve in the space of measures, you expect the syncon divergence between mu t and mu t plus tau to be of the order tau squared. So if you replace your distance squared by something which is still behaves like tau squared, like something of the order of second order close to the diagonal, the two terms in the JKO scheme, in the syncon JKO scheme, they scale well. In the sense that when tau is to 0, the first term is of order, say, tau, and it's approximated, for instance, by the differential of E, and the second term is of order tau squared divided by tau, and so it will be approximated by, well, basically something which depends on the Hessian of the syncon divergence, and so you expect that you converge to an equation which would be like at each time you select the velocity which minimizes the sum of these two terms. Actually, this term, so if you say that the syncon divergence is actually 0 on the diagonal and strictly positive outside of the diagonal, you even expect that this quadratic detachment, so if you look at the second order in the Taylor expansion, this is something so which depends on mu and on the direction mu dot in which you're looking at. So this is and this is a quadratic in mu dot. So that would be a quadratic form on the tangent space to the space of measures. So this is a metric tensor. So with this, I would be able to define a geometry. And so this is this metric tensor defined through the Taylor expansion of the syncon divergence that we will give rise to the geometry of syncon divergence. And then, well, we expect that the syncon JKO scheme converges when tau goes to 0 to the gradient flow of the energy, but in the geometry of syncon divergences. So this was the motivation. The outline is first. In the first part, I just want to go quickly over the metric geometry of optimal transport, and just to be sure that we agree about when I talk about metric tensor and tangent space, what am I talking about? And then talk about the geometry of syncon divergences, and then gradient flow. We will restrict because we only know to do this to potential energies in the syncon geometry. So first, optimal transport. So the metric point of view of optimal transport. So in the sense, for the syncon divergence, I will look at the expansion of the syncon divergence close to the diagonal, just to recall that we know how to do this when you have optimal transport. So the linearization of optimal transport, what happens to the optimal transport when the two measures are close, or a bit simpler, what happens if you have a curve valued in the Wasserstein space and you look at the optimal transport distance between mu0 and mu-t. Well, under some regularity assumption that I will skip, basically, well, this is linked to the Benhamou-Bonnet formula, to the continuity equation. So what you can say is that you can, if you take a curve mu t, which corresponds to a horizontal displacement, that is, you move it with a velocity field. That is the continuity equation d mu t over dt is minus divergence of mu v satisfied. Then you look among all the velocity, I mean, the odd t between mu 0 and mu t is of order t squared when t is small, and you have integral of velocity squared times mu 0. You may have more than one v, which represent the motion of mass, and you select for the minimal one because you are doing optimal transport. And actually, the minimal v, you know that this is a gradient, and it can be obtained by solving an elliptic equation with an elliptic equation. So once you have this, well, the autocalculus or the Riemannian point of view on the Wasserstein space is that a point in the Wasserstein space is a measure. A direction in the Wasserstein space is, so it depends how you define it, but sometimes you just define the velocity field, or you would say the velocity field is the gradient of something, so it's the gradient psi. Or here, and I will focus on calling the direction would be mu dot, which is really the d mu over dt, if you want to think about it as a distribution. But this is, say, a direction is a mu dot, which is given by minus divergence of mu graph psi. And then the metric tensor, which is for every point, for every mu, a quadratic form on the tangent space, is the integral of velocity squared, which is the integral of gradient psi squared, gradient psi being the velocity. Then the fact that you have something which looks like a Riemannian manifold, there is the Benhamou-Brunner formula, which says that the distance squared can be recovered by minimizing the action of curve joining points, or more precisely, the optimal transport distance between 2 points. You look at all the curves joining mu 0 to mu 1, and you look at the action of the curve, which is the integral of the metric tensor evaluated at mu dot, mu dot. And the minimizers are the Wasserstein geodesics. And finally, let me say, regarding the JKO scheme and the gradient flows, this linearization argument that I mentioned, you can at least perform it formally. If you want to, I mean, this is a one way to, say, recover the equation of the Wasserstein gradient flows, which means, well, the linearization of the JKO scheme when tau is small becomes here, so the differential, and here you replace it with the metric tensor. It's not necessarily the best way to derive the equation, I mean, to prove formally the limit, but at least to prove rigorously the limit, but to derive the equation can be one way. Okay, now let me switch to syncon divergences. And here I will follow the same steps, which is I will define the metric tensor by looking at the expansion of the syncon divergence close to the diagonal. And then I will define the distance by minimizing, actually I'll define the distance via the generalization or the analog of basically what is the Riemannian distance or the Benhamou-Brunner formula, which is I will define the distance by minimizing over all curves joining two different measures, the action of the curve. And let me mention here, so work by Park and Slepchev, where they do the same kind of reasoning, but with the sized Wasserstein distance. That was mentioned by Guillaume. So I had a chat with Dejan Slepchev, and it was nice because we studied very different objects, but we had exactly the same questions, so we were able to sort of compare a bit the different behaviors. So maybe this is mentioned by the fact that the motivation was a fake motivation, or we started by saying we started by doing actually only this project without necessarily thinking about gradient flow. I think the underlying topic was, okay, can we define something which really looks like an actual Riemannian distance out of syncon divergence? And actually what will be an output of this is that a distance which looks like optimal transport, but which is much smoother than the optimal transport distance. But I completely agree that for step 3, to do the third part, you don't need the second one. So as I want to look at the behavior of syncon divergence close to the diagonal, I first have to explain you what exactly happens at the diagonal, or more precisely, for the optimal transport, the entropic optimal transport problem for a measure with itself, which is not a trivial problem because of you have a bit of noise. So maybe this slide is better read backwards, in the sense the entropic optimal transport plan between a measure and itself has a density respect to the product measure. This density, I call it K in this K sub mu. This density is actually a tilting of the density exponential minus C divided by epsilon by F mu of X plus F mu of Y. with the same f mu. And this f mu is the Schrödinger potential. So it's a function defined on the space X, and which satisfies this fixed point equation, which is written. So some f mu is minus, and there is a typo. There is a log missing. I think here should be minus epsilon log of this quantity. And maybe some interpretation that also is developed more rigorously in some setting in this article with by Sumik Pal and co-authors, is that by doing this, you're sort of defining a Markov chain which is reversible, whose equilibrium measure is mu, and which more or less looks like a diffusion. So you're sort of prescribing a diffusion to have to be reversible and to have equilibrium measure mu. But the object which is important, so is this k sub mu, which is this kernel, say, induced by the entropic optimal transport plan. Now, the expansion of the synchrone divergence, and we state it for vertical perturbations. So we take a vertical perturbation, that is, I take a measure mu and I add mass somewhere and I remove it elsewhere. So mu dot here, d mu over dt, is for the moment a sign measure. So we have a formula which involves two operators. So h sub mu, which act on measures, and which is actually a mean kernel embedding into the RKHS generated by k mu. I will explain. Which is just, say, a kernel operator. And that k sub mu, which is k mu times, h mu applied to phi times mu, which is another, say, kernel operator. And then the expansion is you take mu dot, which is a measure, you apply h mu, that gives you a function. Then you take identity minus k mu squared, which is basically inverting the Laplacian of the Markov chain I was mentioning, and then you get still a function and you pair it with mu dot. So it makes sense. You are solving an elliptic equation. If you look at it for long enough and that you know about optimal transport, it should really be the right approximation. But maybe also the main message is that we have a formula, which actually you can read in some previous work, for instance, by Niles Wood and collaborators. Not exactly, this formula was in the context where they were doing so statistics and the perturbation were IID sampled from the measure mu. So this formula is not completely new. I don't claim that it is completely new. But what will be different is what we will do out of this formula. And well, the theorem is that you have a detachment which is quadratic, and then so t squared, and then this formula that I was reading is said how it behaves on mu and mu dot. And so, but we take this formula as the starting point in the sense we define g mu of mu dot mu dot. So it's a quadratic form depending on mu and mu dot as well. This formula, which is so this identity minus k mu squared h mu of mu dot paired with mu dot. So once we have this metric tensor, we define the distance by saying I have mu0 and mu1. I look at all the paths in the space of probability distribution which join mu0 and mu1. I will at some point specify more or less the class of path, but I can already say that it includes both horizontal and vertical perturbations. So we are allowed both to move horizontally, or so by a velocity field, or adding and subtracting mass. And for a given class of path, you minimize the g mu t of mu dot, and then this should give you what we call the distance, which depends on epsilon and which depends on the cost function, so ds of mu0, mu1. This gives you the square of it. At this point, let me emphasize that we work on a compact space, and we work on a cost function c, which is not necessarily quadratic. The only thing that we impose is that exponential minus c divided by epsilon defines a positive definite universal kernel. In particular, and the space X does not have to be a subset of Rd. For instance, it works if X is a discrete space. And it can work for other cost functions than just the quadratic cost. Now, this is the theorem that we wrote almost on the first week of the project. So the way the project started is that Bernard was visiting Bocconi, Luca Tamanini was at Bocconi, and in some days of computation on the blackboard, we managed to identify this formula. Then we wrote this candidate theorem that ds is a distance over the space of probability distribution. It should metrize the weak convergence of measure, And well, geodesics exist in the sense the infimum in this definition is attained, and you can really say that you have geodesic joining points. This was written on the first week of the project and proved 6 months after. And maybe more, because more interesting than the theorem is about a bit the proof techniques and a key change of variables. Because say even one difficulty, so to prove, say that it's a distance, it's not so hard, but the geodesics exist and this kind of stuff, you have to do calculus of variations, direct method, you have coercivity, lower semi-continuity, and the question in which kind of functional space do you have access to? Because you are on a compact space, you have the cost function C, but you don't have that much, you don't have, I mean, one difficulty was to understand which functional spaces are the adapted ones. And the key assumption is this exponential minus C divided by epsilon is a positive definite universal kernel. What does it mean? It means basically that it generates a RKHS, a reproducing kernel Hilbert space. So I don't know how familiar you are with this. Me, I really understood what it is during this project. But in one slide, so the fact that, you have KC, so which is the kernel, which is a function of two variables. It generates a reproducing kernel Hilbert space in the following. So it's a space of function over X. This space of function is defined as you take the span of the kernel function if you freeze one of the input. And the dot product between KC of dot X and KC of dot Y is KC of XY. The fact that the kernel is positive definite means that this actually defines a dot product on this space. Then you get something like this, which is a pre-Hilbert space, and you take the completion, and you get a Hilbert space of function. The fact that the kernel is universal means that this space is dense in the space of continuous function. If you take, say, to give fixed idea, if you take X, which is the torus, and C, which is the quadratic cost, this kernel is made of this space of this RKHS is made of very smooth function. It's function basically whose Fourier transform is decaying exponentially fast at infinity. It's like in the Fourier space, the dot product is weighted by exponential of psi squared times, yes, exponential of psi squared. So this is, say, the space, so this is the additional space of functions over which we will be able to do our analysis. Yes? Is the? No, it's the one with completion. HC, say, HC, sorry, is the span, is the completion of the span of this with this dot product. This is a typo, sorry, thank you. Sorry, this is HC. No, or KC universal, yes, no, there is a typo. Yes, so there is, I'm here talking only about only one RKHS. So the key, the magic trick is a change of variable, which if you read the article by Fedi, Séjourné, and co-authors, I think it's François-Xavier Vialard who saw this change of variable. It's not the article is not written in this form, but it's a key change of variable, which is take a measure mu, compute the Schrödinger potential f mu, and take exponential minus f mu divided by epsilon. First claim, this belongs to the RKHS. So this is B, the variable B, it's a function over X, and it belongs to the RKHS. Moreover, it belongs to the unit sphere of the RKHS. And this is related to the fact that mu has norm 1, mu has total mass 1. And moreover, actually, you also have, it belongs to a positive cone in the RKHS, in the sense it's the cone generated by the mean kernel embedding of positive measures, so it belongs to a cone which corresponds to positivity of the measure. So you do a change of variable which maps the space of probability distribution in the intersection between the unit sphere of the Hilbert space and we intersected with a cone. And this change of variable, first, it's a homeomorphism. It's continuous with continuous inverse. Then, this is for the, say, topological properties. Then if you go to the differential property, so I never remember if it's the pullback or push forward of the metric tensor, but you have a metric tensor on the space of probability distribution, and you can look at what is it, the induced metric tensor on the RKHS. In the sense, if you have a curve in the space of probability distribution, you lift it as a curve via this change of variable in the RKHS, And it gives you, well, the metric tensor, you can compute how it translates into G tilde, so which depends of mu t, or here it could be bt and b dot b dot. And this metric tensor in the RKHS is jointly continuous in mu and beta. So the metric tensor depends smoothly on the base point, and also it compares uniformly to the flat norm on the RKHS. That is, it is comparable to b dot squared, the norm of b dot, uniformly in U. Note that already here, just by doing this change of variable in the RKHS, I have a common tangent space, because every b dot belongs to the RKHS. I am in the RKHS, it's a vector space, so I can b dot belongs to the RKHS. So I have a language to talk about the tangent space. I mean, at every point, the tangent space is included to the hyperplane perpendicular to B, but I have a common language to talk about the tangent space. And even more than this, what it's saying is that the space of probability distribution seen in the RKHS, it's basically, so it's a submanifold of the unit sphere, and with a metric tensor which is not flat, but which compares to the flat norm, and which is jointly continuous. So for instance, what are the admissible paths in the metric? So what are the admissible paths for the problem defining geodesics? I do the change of variable in the RKHS, and then I need to have a path which is H1 valued in a Hilbert space. So yes. Yes, mu can be a Dirac mass. So here, I mean, we're on a compact space. But yes, mu can be a Dirac mass. Mu can be a Dirac mass. I mean, the intuition is that even if you have a Dirac mass, when you do entropic optimal transport, you at some point you have the kern. I mean, the Dirac mass, for instance, in this will be represented by a function which is exponential minus f mu. It will be represented by a kernel function. Will be a Dirac mass will be mapped to k of x dot. Yeah, so then in the RKHS, so the path is H1 valued in a Hilbert space. This we will understand what it is. Also, the distance is comparable to the distance in the RKHS. So the distance that we define is comparable to the distance in the RKHS, which actually, if you think optimal transport distance, to compare an optimal transport distance to, say, another distance. Well, for instance, there was the talk of Quentin Mérigot about how you can do this kind of comparison, but the one of Guillaume with slice Wasserstein distance, or sometimes you can compare an optimal transport distance with a negative Sobolev norm, but you always have to put restrictions. Here in this case, we have something which, well, the only price that we pay is that the constant depend on epsilon, and that even the space depends on epsilon, but we compare, say, we understand better our distance, and we compare it to a nice flat distance on the Hilbert space. So I will not say do the full proof of existence of geodesics, but maybe you can believe me that once you go in the RKHS, you are not completely done, but at least you are doing calculus of variation in the Hilbert space with an integrand which is jointly continuous. You need a little bit more of properties, but you do, I mean, it's more classical. And I will not do this because I'm saving a bit of time to talk about now gradient flows in the so potential energy in the synchrone geometry. Okay, so what am I talking about? So now I go back to the motivation, which is the synchrone JKO scheme. So I take the synchrone JKO scheme, I minimize, so E, which is an energy, which I take only a potential energy. So E of mu is integral of V d mu. Here I am on X, a compact space. E, V will just be a continuous function. But if I take quadratic cost, V, which is a, say, C1 function or convex function, and that I look at the epsilon equal to 0 classical optimal transport, of course, to recover the transport equation. And then what I want to understand is what's the behavior when epsilon goes to 0. As I said, as we have the metric tensor, you can formally pass to the limit tau goes to 0, and you obtain an evolution. I mean, you can write formally what is the evolution equation. Okay, so you replace basically S epsilon by this expansion, you take tau goes to 0, and you get formally what is the equation. So you have this operator k mu and h mu, and the equation is, so you have an identity minus k mu squared minus 1, h mu of mu dot plus v, plus p, which is a function which is a pressure, which has the property of basically being active, which has a sign and which is active only outside of the support of mu. Why do you have a pressure? Because here vertical perturbations are allowed. So you need to enforce that vertical perturbation will not make you leave the space of positive measures. Okay, so this is the equation. And actually, if you look at the equation, it's very bad. Why? Because the equation, if you rewrite it, it's basically h mu of mu dot is equal to something. So it's mu dot is equal to h mu minus 1 of something. And h mu is, say, convolution with the kernel k mu. Even if you think that here we replace k mu would be exponential minus c. So think about h mu as convolution with a Gaussian, so that your equation is mu dot is the deconvolution of something. So well, it's non-local, but also it's of basically formally infinite order, because you can have, the deconvolution of a very smooth function can be very non-smooth. And when I talked to Dejan Slepčev, so he made me this remark that is the smoother the metric tensor is, because the metric tensor of Syncon is very smooth, it can have a very large class of perturbations. So the smoother the metric tensor is, the worse the gradient flow will be, in the sense the more ill-posed the gradient flow will be. So he said, you will see, it will not work. But in the case of this potential energy, we managed to make it work. And without a surprise, the trick will be to go on the Hilbert space. So then we do the change of variable, that is, we look at rather the evolution, what happens in the Hilbert space. Well, we do the change of variable, we rearrange the term, and we have b dot plus 2 over epsilon, v times bt. So it's multiplication of the function b by the function v, the potential. And here you have, I write v star times bt, which will be a linear operator, which is the adjoint of multiplying by v for the product in the Hilbert space, plus the pressure is equal to 0. So here I met asterisk. V is actually not, v times b is not always stay in the Hilbert space. So it's basically an unbounded operator, but we don't even know if it's self-adjoint. So it's a bit, you have some subtleties here that we make sense of this equation at least as continuous functions, whereas not everything can be made sense of in the Hilbert space. But now if you analyze the structure of the equation, what is it? You have bt plus v minus v star bt, bt dot plus v minus v star bt. V minus v star is basically a skew symmetric operator. So it generates a group of unitary operator. If you want, it generates a rotation. So that is, me, I was very excited, very surprised. You start with a gradient flow. You do a change of variable in the Hilbert space. You change the geometry, because here I'm looking at the flat geometry of the Hilbert space, whereas normally here I would have the metric tensor of on the Hilbert space, but I'm just looking at what's happening if I look with the flat geometry of the Hilbert space, and I obtain a rotation. Then it's even too suspicious, because rotation have a tendency to be periodic. Gradient flow cannot be periodic. However, I have a second term, which is the pressure. And the pressure is basically, I need to keep the positivity. And in the geometry of the Hilbert space is the subdifferential of the convex indicator of staying in the cone. Okay, so this is the pressure which will maintain in the cone. It also means that the structure, which is this Q-symmetric operator, plus the differential of basically a convex function, I have a maximum. I have a monotone operator, or I think so related also to Julia's talk on say dissipative operator. But I have something which has a nice mathematical structure. Here the picture is very abstract. There is, and Mathis made me the remark that there is one case where the picture is exact, where I can really do an exact drawing, and here it's a simulation, which is the case of the 3-point space. So I take a space with 3 points. So the space of probability distribution is the simplex, the triangle, and I put it on, and then the Hilbert space is 3-dimensional, and it's really a triangle on the sphere. And here I'm really saying that on the sphere, I have a rotation movement, and then I am constrained to stay in the triangle. So here it's a simulation. So you start from here, a point with mass everywhere. Then you follow the rotation. And then when you hit the boundary, what will happen is that you have a constrained motion, so you want to follow the rotation, but you have to stay on inside the triangle, and so you will move upward the boundary at the velocity. Here it's almost orthogonal, not exactly orthogonal, so you will move upward the boundary until reaching this point, which will be the point of minimum of V. Okay, so in the 3-point space, it's exact. This representation is really a constrained rotation. What can we say about this formal limits of the syncon flow, at least, let's say, this equation? Everything. More precisely, existence, uniqueness, long-term behavior. So what we have is existence. The syncon flow is well defined in the sense for every initial condition, there exists a syncon flow defined for arbitrary long time. The way we prove it is we actually take our space, approximate it with a finite space, and when we are on a finite space, all the subtleties of functional analysis disappear, and we really have a maximal monotone. We have the maximal monotone evolution. We have the evolution of a maximal monotone operator. This is well understood. We have existence for the finite space, and then this is where we need to pass to the limit. It's technical, but we manage to pass to the limit and to get existence of a solution by passing to the limit what's happening for a finite space. Uniqueness, do we have uniqueness? Yes, we have even more. We have non-expensivity. Because this is a maximal monotone evolution, so this is non-expensive. Well, you can basically do the computation. You take the difference of the norm between two solutions, and then it decays. So not only we have uniqueness, we have non-expensivity. But here, note that it's non-expensivity in the norm of the Hilbert space, whereas we are taking a gradient flow with respect to the geometry of syncon divergences. So in particular, my potential is not convex. My potential is any continuous function. So my potential is not convex, it's not geodesically convex. There can be any, say, continuous function. I could even take a potential which is non-convex in the geometry of syncon divergences, and I get a flow which is contractive, but not in the geometry of syncon divergence. I get a flow which is contractive in the flat norm of the Hilbert space, which is metrically equivalent, which is comparable up to constants to the distance, to the Riemannian distance, but I get this non-expensivity. Finally, long-term behavior. What we have is convergence to a global minimum. So the energy is a potential energy. And well, as time goes to plus infinity, the energy of μt converges to the minimum of the energy. And here the intuition, whereas for the classical gradient flow, the Wasserstein gradient flow, which is the transport equation, you will converge to local minima of V, but you will be trapped into local minima. And here the reason is that in the geometry of syncon divergences, we are allowed vertical perturbation, and vertical perturbation enable us to escape critical points of V. So basically, what we say is that there exists at least an accumulation point of the gradient flow, and then it is a critical point for the geometry of syncon divergences, and then the only possible critical points are the global minima of the energy. And so here it means that V, again, so these results are not related to the convexity properties of V. Two examples to illustrate that actually this gradient flow sometimes behave like horizontal motion, sometimes behave like vertical interpolation. First example, which is theoretical, which is when you start from a Dirac mass. So imagine you start from, when you recover a classical flow. So if you start from a Dirac mass, and if the potential V is convex, and if you take the quadratic cost, then the syncon flow is the same as the Wasserstein gradient flow, is the same as the classical flow. That is, you follow x dot is minus gradient V of xt. And so, but the potential is convex, so you converge to a point of global minimum, and so there is no problem. And so here you really see a horizontal motion. Now, numerical simulations obtained via the syncon JKO scheme, which is take a potential which has local minima. So this is the potential here on the right in blue. The global minimum is on the bottom left, and you start with mass on the top right. Then what's happening is that what you see, you know that normally in long term, you will converge to a Dirac mass more or less located here. What you observe when you see the evolution is that the mass will actually jump over, so will follow a vertical motion and will jump over the high points of the potential. And so you get something which more or less looks like a vertical interpolation. I mean, only vertical motion, that is, mass is getting teleported, which is what's happening. And which also hints that if you try to simulate the Synchron gradient flow with just a Lagrangian discretization with particle family, you will have trouble because it will be hard to make the particles teleport. So it's also, yes, the Synchron flow converges to a global minimum. Then can you implement it? That's another challenge. Here it's implemented on the grid. And on the grid, well, it's, you can teleport. But then if you're interested in minimizing V and you have to evaluate V on the grid, there is a much faster algorithm to find the minimum point of V on the grid. You just enumerate the point on the grid and you look what the value is the minimum. Last thing that I want to say is actually to close the loop, because I started to say, well, everything you wanted to know about the Synchron JKO scheme. And we don't, it's not every, I mean, we would like to know more. In the sense that, so I started to say I have the Synchron JKO scheme, I have done the change of variable, and I have looked at the Synchron flow. And what we have said is that this equation, the Synchron flow, we can analyze it. We know most of its properties. Then the question is there a link between the two? And the answer is, for the moment, we are only able to prove it when the space X is finite. So when you have a finite space, we are able to say that if you take the solution to the SJKO scheme and you interpolate them properly in time, then when tau goes to 0, the solution to the SJKO scheme converges to the Synchron flow. X is finite makes us disappear all the subtleties of functional analysis, because then we are dealing with a finite dimensional vector spaces where all the topologies and all the norms are equivalent, whereas when you are on an infinite dimensional space, we have issues. So we are still working on, it seems to be like a quite difficult problem to really get the convergence in the case of a space which is an arbitrary space. So this is more or less what I wanted to say. So there is a few topics that I have not, so something more on the geometry of Synchron divergence that I have not presented. So some explicit computation, some counterexample of some properties that were thought to be false but not necessarily written. And then we sort of have a lot of still work to do. So for instance, what happens to this gradient flow if you go beyond potential energies? What happens if you put the entropy? We don't know. We don't know if the change of variable will really, it seems to behave a bit less good. Also, we will have, say, numerical approximation of the geodesics, say, for the more the geometry part. What happens when epsilon goes to 0? Formally, we recover the good limit. Which kind of limit we can really prove? And let me add something which is not on the list, but it's also what happens when you do unbalanced Synchron divergence, because then in the sphere picture, what would happen is that instead of being on the intersection between the cone and the unit sphere, you just should be on the cone. But this is all work in progress, and I will stop here and thank you for your attention.
Thank you very much, Hugo. Do we have questions? A couple. Yep.
Thank you for the talk. Do you have any ideas what happens in non-compact setting? So probably you lose comparability between distances, but what else?
So I think it's when you go to a non-compact space, all the so for instance, the Schrödinger potentials are not uniformly bounded, so that we have a lot of estimates. Then, I mean, it may be possible to refine the estimates, but a lot of arguments are simplified by the fact that the constants are uniform on the base point. So, I mean, I don't know what can be really done. I think some things can be done, but it was already, there was already challenging. I mean, for later, say, for later. But basically, yes, a lot of constants that we have are not uniformly controlled. So then maybe you know you need to have some control by other arguments.
Thank you.
The sink or flow is also a gradient structure, or is just a monotone evolution?
So the sink on flow has a gradient. It's a gradient flow. So it's a gradient flow, but for the metric tensor, which is so maybe let me go to this picture. That is, when you go to the Hilbert space, you can put on the space here the flat norm, or you can put the metric tensor, which is induced by P of x. So what I'm saying is that it has a structure of gradient flow with respect to the metric tensor induced by the one of the syncon divergence. This is even this is how we derive the equation of the gradient of the syncon flow. But then on the same space, but if you do the flat norm, the flat structure of the Hilbert space, then this is this maximal monotone evolution. Up to problem with domains that the operators are not self-adjoint and so on. So say. But it has this structure, this V minus V star plus indicator of a convex function, subdifferential of a convex function.
Yep. Simone.
Thank you. So very nice. Thank you for the talk. And so my question is actually very similar to the one that Nicola said before, but maybe because I don't understand really this map B. So you're saying that B, so it's exponential minus f mu over epsilon, right? But f mu is defined only on the support of mu, right?
So in this case, so okay, maybe because exponential minus f mu, I take epsilon is equal to minus f mu, I take epsilon is equal to 1. It's actually by the Schrödinger system, it's the integral of exponential minus c times exponential f mu times d mu. C, I mean here of x, y. Here, say you integrate in y, and here you have of x. And so first, that's by this formula, it's defined everywhere. So it's basically we use the fact that we can always define in a non-ambiguous way the potentials everywhere. And also you see that basically this is the convolution between between the kernel exponential minus c and the measure mu exponential f mu.
Okay.
So which means that this is actually this quantity is the mean kernel embedding of mu exponential f mu. So that's also why it belongs to the Hilbert space.
Okay, so I look at the one at the right is defined mu almost everywhere.
Yes.
But then the one on the left,
yes,
it's defined everywhere. And okay, very clear. Thank you.
I think it's time to move to the next talk. So let's thank you once again. All right, we can continue with the second talk of this afternoon. It is my pleasure to introduce Daniele Semola from Vienna. And as you see, he's going to speak about the topology of three-dimensional RCD spaces, open results, and open questions. Please,
Thank you very much for the introduction. Thank you very much to the organizers for the invitation. It's really a pleasure to be again in Pisa. So as said, I'm going to speak about the topology of three-dimensional RCD spaces. And all I'm going to talk about is based on joint work with Elia Bru and Alessandro Bicati, who are both now at Università Bocconi in Milan. So let me start by setting some notation. So we are going to fix for the rest of the talk 3 parameters. So n is going to be a natural number, and it's going to denote a dimension. Then we are going to fix a parameter d, which is a real number, positive. D is going to stand for diameter. And we are also going to fix a parameter little v, positive, and little v is going to stand for volume. And I'm going to be interested in the following two classes of objects. So I'm going to be interested in sectional and V, D, V. This is defined to be the class of all smooth and dimensional Riemannian manifolds, M and G, such that the sectional curvature of this guy is greater or equal than -1. And then I want the diameter of the manifold to be less or equal than D. And I want also the volume of the manifold to be bigger than little v.
Okay, and I'm also going to be interested in the counterpart of this family for Ricci curvature. So I'm going to denote by Ric and the V, the class of all smooth Riemannian manifolds, M and G, with dimension n, such that the Ricci curvature, this time it's nicer to normalize it to be greater or equal than minus n minus 2. And then I'm assuming that the same bounds hold for the diameter and the volume. Okay, now a famous theorem of Gromov, the so-called Gromov's precompactness theorem, says that these two classes, okay, they are pre-compact with respect to the so-called Gromov-Hausdorff topologies. Okay, and my goal for the rest of the talk, so the question I'm going to be interested in is understanding how the closures of these two classes with respect to the Gromov-Hausdorff topology look like. Okay. Okay, any questions? Okay, so let's start from the basic things. Okay, so I put in the definition of the two classes a lower bound, a uniform lower bound on the volume of the objects. And what's the role of this lower bound on the volume? The role is preventing collapsing. Okay, so the first observation is that any metric space XD in disclosures has the same dimension of the smooth Riemannian manifolds in the two classes. Okay, and here as dimension, I'm picking the Hausdorff dimension. Okay, and this is due to Burago, Gromov, and Perelman. In 91, in the first case, in the case of sectional curvature, and it's due more recently to Chigger and Kolding for Ricci curvature. Okay, so this is the first observation. And now, if I want to say something more precise, then I need to invoke the so-called synthetic theory of lower curvature bounds, either for sectional curvature or for Ricci curvature. And here what happens is that in the first case, so the closure of smooth Riemannian manifolds with the sectional curvature bounded from below, this is contained in the class of Alexandrov spaces with dimension n. Sectional curvature bounded from below by -1 in the sense of triangle comparison, and diameter less or equal than d, and volume bigger or equal than v. Okay, so those are Alexandrov spaces. Okay, and on the other hand, in the case of Ricci curvature, okay, this closure is included in the class of RCD spaces. So. Okay, and let me employ an unusual notation. So, and stick here just a dimension, the upper bound of the diameter and the volume. Okay, and this topic is a good fit for the conference because the definition of this class that I'm not going to explain is based on optimal transport, and several people in the audience contributed to it. So let me just recall what these three letters stand for. So R stands for Riemannian. C stands for curvature, and D stands for dimension. Okay, and here the understanding is that limits, so guys in disclosure are metric spaces, XD. Okay, and the requirement is that if I endow this metric space with the Hausdorff measure of dimension n, okay, then I would like this guy to be an RCD minus n minus 1 n space. Okay, well, the role of the two parameters is that the first parameter plays the role of the lower bound on the Ricci curvature. So I'm taking the closure of the set of manifolds with Ricci bounded from below by -1, n minus 1. Okay, and this guy should have a Ricci curvature bounded from below by n minus 1 in synthetic sense. Okay, and the second parameter plays the role of the dimension. Okay, so let me replace the question now that I stated before. Okay, now the question becomes, I have these two inclusions. Okay, are they strict? Okay, so for n equal to 1, the problem is almost trivial. For n equal to 2, we know everything. So if you ask me a question about n equal to 2, I can answer to that. Okay, and I'm gonna mostly be interested in the case n equal to 3. Okay, and the answer is that the two inclusions are strict. Okay, and I can give you an example. So consider S3 with the standard round metric. So this is S3 G round with radius 1, let's say. Okay, now you pick an involution with two fixed points, the North Pole and the South Pole. So I from S3 to S3 involution. Okay. Now the claim is that if you look at the quotient of this nice smooth Riemannian manifold with respect to this involution, the guy that you get belongs to the right-hand sides, but it doesn't belong to the left-hand sides. Okay, and morally, the reason is that this quotient is not a manifold. Okay, so the reason is that there are this isometry, this involution has two fixed points. If you look at the images of these two fixed points under the projection to the quotient, they're not going to be manifold points. Okay, and relying on this idea, so Grove, Petersen, and Wu in 89, okay, proved first that this guy doesn't belong to the left-hand side in this case of sectional curvature. Okay, this was in 89. And later, Zhu in 93. Yeah. That's right. Yeah. So later, Zhu in 93 proved the same statement. So this guy doesn't belong to the closure in the case of Ricci curvature either. Okay. A few years later in 93. Okay. Any questions? Now, let me rephrase the question. So the question now becomes how can we fix this? Okay, so now it's clear that the classes that I put at the right-hand side, they are too large. And I would like to work from both ends. Okay, so I would like to get some new conditions on the classes at the left-hand sides and get a practical way to check whether these conditions hold when staring at the guy in the right-hand side. Okay, so let's discuss the case of sectional curvature first. Okay, so here we can rely on the so-called Perelman stability theorem that Perelman proved in 91. Okay, and the statement says that in any dimension, okay, any element in the left-hand side for sectional curvature is a topological manifold. Okay, so this works in any dimension, and we have a counterpart for that in dimension 3 in the case of Ricci curvature. This is due to Simon more recently. Due to Miles Simon in 2012. Okay, and the statement is that the same is true for n equal to 3. Also, xd in the closure of manifolds with Ricci bounded from below is a topological free manifold. Okay, so good enough. So at this stage, we know that all the elements in the closures at the left-hand side, they are topological manifolds. For any n in the case of sectional curvature, and for n equal to 3 in the case of Ricci curvature. And let me also point out that there are counterexamples for n greater or equal than 4 in this case. Okay, and as I said, the second thing that I would like to do is to get a criterion to check whether an element in the right, so in the class at the right-hand side, is a topological manifold or not. Okay, and for that I need some background. Okay, so I need to tell you what a blow up or a tangent cone of an element at the right-hand side is. Okay, so let me fix n equal to 3, but this doesn't really matter for the first part of the discussion. So we fix x d h3 and RCD minus 2, 3 space. Okay, then we fix a point, little x, in capital X, and a sequence of radii going to 0. Okay, and then what I can do is to look at my space, rescale along this sequence, and pass to the limit. Okay, and what I'm gonna get, I'm gonna call a blow up of the metric space. Then we consider x, this is fixed. I rescale the distance by the parameter ri to the minus 1. I endow it with the newly rescaled out of measure, and I fix a base point. Okay, so if this sequence converges to the limit, okay, and this is always the case up to subsequences, okay, then the statement is that the limit is gonna be a cone. Okay, and I won't give the precise definition of a cone. The cone is what you think is the right notion of cone, and this cone is gonna have a section, and this section is two-dimensional. Okay, so this is due to De Filippis and Gigli. In 2016, in this setting, and it was proved before by Burago, Gromov, and Perelman. In the case of sectional curvature bounded from below, and by Chigger and Colding in '97 for elements in the closure of in the class set of the left-hand side here for Ricci curvature. Okay, so the second thing that I need is that in dimension 3, which is the dimension I care about, okay, so these cones are really special. Okay, and what's the reason? The reason is that Lichak and Stadler in 2019, okay, they proved that there are 3 options for the topology of the section. Okay, so they prove that Z is a topological surface. Okay, and it can be either homeomorphic to S2, okay, in which case the cone is clearly homeomorphic to R3. Either it is homeomorphic to D2, the 2 disk, in which case the cone over it is homeomorphic to half space. Let me write it. Okay, and there is a third option, which is the 2-dimensional projective plane. In which case the cone doesn't have a clean expression. This is just the cone over RP2. Okay, you can equivalently think of it as being the quotient of R3 with respect to the same involution basically that I introduced before. Okay, any questions? So now I can give you the criterion that I promised. So this is due again due to Perelman for Alexandro spaces. Okay, so this is the so-called Perelman's conical neighborhood theorem. Okay, and again, it holds in any dimension. So if X, D belongs to the class of Alexandro spaces with dimension n, and let me drop the other 2 parameters, any X in X has a neighborhood Ux homeomorphic to the tangent cone. Okay, and the counterpart of this criterion in dimension 3 for Ricci curvature, this is due to Brouet, Pigatti, and myself this year. Okay, and again, so as I said, Perelman's theorem holds in any dimension. This theorem that they're going to state can only hold in dimension 3. So for X, D, H3, which is an RCD -2, 3 space. Okay, we don't have a criterion for the moment which is as sharp as Perelman's criterion, but we can say that XD is a topological free manifold. If and only if, please. Say it again. Yeah. No. So it gives you a criterion to check. Okay. So for instance, in the example of the quotient of a S3 modulo di involution, okay, if you do the blow up, this is going to become the cone over RP2. Okay, Perelman tells you that the point has a neighborhood homeomorphic to the cone over RP2, and in particular, it is not a manifold. Okay. So this space is going to be a topological free manifold if and only if all blow-ups are homeomorphic to R3, or equivalently, all the sections of all blow-ups are homeomorphic to S2. Okay, any questions? At the boundary, we are not able to treat that. Okay, so the boundary, so the boundary will be homeomorphic to R3 plus. Okay, any more questions? Okay, so now we can go back to these inclusions here. Okay, so let me do this. So let me put a 3 here. Okay, so we know that all the elements in these closures are topological manifolds, so I can intersect with the topological manifolds. Both above and below. Okay, so now if you would like this inclusion to be an equality, better for the right-hand sides to be closed. Okay, but this is true. Okay, so Perelman proved it in the first line. So and with degli and Alessandro, we proved it for the bottom line. So the right-hand sides are closed. Okay, so now I can ask again, are the inclusions strict? Okay, and the answer is that nobody knows. Okay, so for the first line, okay, the problem has been around for the 80s, and in the paper by Burago, Gromov, and Perelman that I cited a few times, they already wrote in 91 that the problem was difficult. Okay, and it still is. Okay, for the second line, the problem has been around for less time, but still it's open. Okay, so I have 5 more minutes. Okay, so now one might wonder whether so it's possible to maybe refine some of the restrictions that we got. So as you have seen, so the statements that I gave were purely topological. Okay, however, we are dealing with metric spaces, and so it's reasonable to wonder whether one can maybe quantify the regularity of the homeomorphism that are involved in the statements. And let me review the state of the art. Okay, so for sectional curvature, Perelman, so he claimed, and the proof never appeared, that, so let me call Perelman's claim, let me call it Perelman's claim or conjecture, let's say. Okay, so the claim is that for sectional curvature, you can let all this, both statements become, so you can improve them from homeomorphic to bi-Lipschitz homeomorphic. Okay, so elements in at the left-hand side are bi-Lipschitz homeomorphic to smooth Riemannian manifolds. Okay, and now you can wonder whether this is a more precise environment, and this maybe makes the inclusion strict. Okay, and this is not the case. The reason is that he also claimed that one could make the conical neighborhood theorem by Lipschitz. Okay, and what happens in dimension 3? In dimension 3, it's not that difficult to check that all these cones, they are by Lipschitz to R3. So if you believe Perelman's claim, also any element at the right-hand side is going to be by Lipschitz homeomorphic to a smooth Riemannian manifold. Okay, so what happens for Ricci curvature? Okay, so in the theorem due to Miles-Simon that I mentioned before, so one can make the homeomorphism by order. Okay, and with the and Alessandro, we conjecture that so that the same should be true in the setting of our theorem. Okay, what happens in the Lipschitz category? So if you move to Ricci curvature, no matter whether you start at the left-hand side or you start at the right-hand side, okay, please. So in Simon's theorem, what happens is that if you want to make get alpha closer to 1, you need the constant to blow up in the by-order homeo. Okay? Any more questions? Okay, so as I was saying, so let's get into the Lipschitz category when in the case of Ricci curvature. So no matter whether you start at the left-hand side or whether you start at the right-hand side, okay, so in general, the existence, not even the existence of a single point with a neighborhood which is by Lipschitz homeomorphic to an open set in R3 is known in the setting. Okay, although Chigger and Colding conjecture that there should be many. Okay. And in particular, the existence of an open and dense subset locally by Lipschitz to R3. In any dimension. Okay, but my point is that so in dimension 2 is true, in dimension 3 we don't know. Okay, and with that I stop here. Thank you for the attention.
Thank you very much, Daniele, for your talk. Are there further questions?
Sorry. The conjectures from Perelman, the last set that you mentioned, are they also from 1991, or when are those made?
Around that time. So apparently Perelman wrote a sketch of the proof in a letter.
I see.
That was sent to Burago and then disappeared.
Okay, thanks.
So, it was in the 90s.
Yes, and there are claims of people working in the field that would love to have access to that letter, as far as I know, right? But apparently that's... Other questions? Maybe actually I have one. So I know that Simon's paper, I mean, the topological rigidity is proven through Ricci flow techniques.
Yeah.
Could you, maybe in a sentence or two, if possible, I mean, what is behind your theorem? So is GMT, I don't think it's Ricci flow, right?
No, it's not Ricci flow.
So
a lot of...
possible to... yeah, I don't know.
So a lot... I can try to explain. Okay, so it involves a lot of three-dimensional topology.
Okay.
Okay, so and in particular, it involves the solution of the Poincaré conjecture, even in the simplest possible case. Okay, so not of the Poincaré conjecture of the statement. So the simplest possible case for me is the case where your RCD space is a smooth Riemannian manifold.
Okay.
Away from a single point.
Okay.
Okay, so let's pick X3, the smooth away from X. Okay, and I only tell you that the blow up at X is homeomorphic to R3.
Okay.
Okay, so here the guy, if you rescale it, is looking more and more like a cone over S2. Okay, however, I don't tell you anything about the metric on the section. Okay, now the idea is the following. So you look at the section. Of course, Gromov-Hausdorff convergence tells you nothing about the topology in general. Okay, but so in dimension 2, it tells you something. So the idea is that you try to copy the section inside the space. Okay, and you try to do that at every scale. So here you have a bunch of S2s that are nicely embedded inside your space. Okay, and they kind of converge, shrink into the point. Okay, now the idea is that, so what you need to prove is to prove that the region bounded between these two guys, okay, this you would like to be homeomorphic to S2 times an interval.
Sure.
Okay, but even in this very simple case, the only thing we can prove is that this region is simply connected. Okay, and to get from simply connected to homeomorphic to S2 times 0, 1, you need to rely on the Poincare conjecture. Okay, but once you have that, you can like glue all together this homomorphism. Okay, and build the homomorphism with the neighborhood of R3.
Very nice. Thank you. Are there further questions? Yes, yeah. Simone. Could you? Sorry? What about R2 was the question?
What do you mean? So in dimension 2? Okay. So sure. So you're asking about the two-dimensional version of the statement? Okay, so that's true. And you can make it, so if in dimension 2, everything is much easier. So if you look at the blow up, it's going to be a cone over a one-dimensional guy. And there are only two possibilities. Okay, it is a circle or it is an interval. Okay, an interval is going to get you a boundary point, and the circle is going to get you an interior manifold point. So what you prove in the end is that the guy is a topological surface. Okay, but it's also possible to prove that such topological surface is by Lipschitz to a smooth Riemannian surface. Okay, and moreover, it's also so if it has boundary, it is a limit of spaces with boundary, which are smooth. Okay, and if it has no boundary, it is a limit of smooth surfaces with the Gaussian curvature bounded from below. This is due to Alexandrov in the 70s or 80s, I think. They are clearly equal, exactly. They are equal, yeah. And they are equal, and if you care about the regularity of the homeos, you can make them by Lipschitz.
Okay, I think it's time to stop. Let's thank Daniele once again. All right, it's time to start with our last talk of today. It's my pleasure to introduce Kimia Najai. She's coming from CNRS and the Columna Superiore, and is going to speak about sliced varsity and distance for generative modeling and unbalanced optimal transport. Please, the stage is yours.
Thank you. Thank you for the introduction and for the invitation. It's an honor to be speaking here at this workshop. So yeah, I've mostly studied optimal transport from this slicing perspective. And so I'll be giving a talk about some theoretical perspective on this metric. And this is inspired by some machine learning applications and generative modeling. And then I will also discuss a recent application that we did where we combine elements from slicing and unbalanced optimal transport. So I just start with a brief, like a broad motivation about the limitation of the conservative optimal transport problem or optimal transport problem in general. So this is a definition of the problem. And so it's known to be hard to solve in general, especially when the distributions are highly dimensional. And so this is a limitation in some applications where we have a lot of samples and high dimensional samples. So usually in this situation, it's encouraged to use surrogates instead of solving this problem directly. Another limitation is that by definition, the mass is preserved when we perform the transportation. And so we need to compare, when we compare two measures, there's a need to have equal mass. So alpha and beta should have the same mass. And in other words, this means that this formulation is adapted to measures that are probability measures. And so if we want to use optimal transport to compare arbitrary positive measures, it means that we need to do normalization operations beforehand, and so it can make the optimal transport problem sensitive to noise and local variation of mass, so it's not ideal. And then another limitation is that we transport all the samples from alpha to beta with this formulation, and maybe in some application you have outliers, meaning that there are some samples from alpha that you don't want to transport, and so you want to discard some undesirable samples. And so there's a need, maybe in these situations, to have a more robust transport problem. And so throughout my talk, I will be talking about the concept of slicing and balancing optimal transport. And these are two formulations that solve these issues. So I'll start with some background on slice optimal transport and some results that I had throughout my PhD mostly. So fortunately, Guillaume talked about it yesterday, so maybe I can be quick on this slide, but just a brief reminder. So the slide of social distance was introduced by Marc Bernot back then, and then published in that paper by Julien Rabin and co-authors. And so we are given the unit sphere in RD, and we define this linear mapping theta stars, which basically consists in projecting a vector x along a direction theta that is on the sphere. And so the Wasserstein distance is simply the expected value of the Wasserstein distance evaluated between random projections of alpha and beta. And so we compute this expectation over the uniform distribution on the sphere that we denote by sigma. So I think the first theoretical results that were derived around the Wasserstein distance appeared in Nicolas Bonnete's thesis that Guillaume mentioned yesterday too. So this is a metric on the space of d-dimensional priority measures. We also have this inequality on the same space. So the Wasserstein distance is lower than the Wasserstein distance. And on measures that are compactly supported, you can have the reverse inequality up to a certain exponent that depends on the dimension. So in Nicolas Bonnete's thesis, it was in 1/d+1. And so if you followed Guillaume's talk yesterday, now there's a new exponent that is in 1/d, and an extension to measures that have finite moments too, if I'm correct. But in any case, this means that on some restricted spaces of measures, the two metrics are equivalent, which is good news in some applications. And so why the community of practitioners got interested in it recently, it's because the computational properties of Wasserstein distance are interesting. And so it's interesting because, okay, first we have an integral that we can approximate with just a Monte Carlo approximation. So we pick a finite number of samples from the sphere, theta, and then we approximate the integral with the average. And then we can solve the optimal transfer problem in 1D, which is easy to do because there's an analytical solution. And if you have discrete measures supported both on n samples, then the optimal transfer problem can be solved by sorting the samples. And so overall, the computational complexity scales in this. So we have the cost of projecting along the k directions that we picked. And we also have the cost of solving the optimal transport problem in 1D. So this is a sorting operation. And so this is, depending on the value of k, d, and n, this is usually much cheaper than solving the Wasserstein distance, solving the optimal transport problem directly between the d-dimensional measures. So that's why it was very popular for people that are more interested in applications with large number of samples and high dimensional data. And so it started with image processing applications with these papers, and then slowly moved to generative models. So this is a type of machine learning problems where you want to basically generate, learn a way to generate data that come from more complicated distributions. So for example, natural images. And so back then when I started my PhD, so in 2018, it was becoming more and more popular to use slice Wasserstein distance as a surrogate measure to Wasserstein in these applications, generative modeling. But the theoretical insights were not really understood. So we, these algorithms were not theoretically grounded. And so we wanted to add more theoretical understanding around these models. So first we got interested in this problem, which is very classical in statistics. So this is the problem of minimum distance estimation. And so let's say that we observe n samples 1 to n that are sampled from an unknown distribution mu star that we wish to approximate. And so to do that, you can minimize a certain distance or divergence d between the distribution that you observe based on the n samples and a parametric distribution. And so the goal is to find the best parameters, so the parameter that fits the best the distribution that you want to approach. And so depending on the distance that you use, you will get different properties. And basically, you can think of this problem as a generalization of maximum likelihood estimation, because when you use D as the KL divergence, this is what it boils down to. And so some generative models can be framed as this problem with D equal to the Slice-Wasserstein distance. And so one thing that we studied were the asymptotic properties of the estimators that we obtained through the Slice-Wasserstein distance. And so we're able to show under some assumptions on the way the data is generated and the identifiability of the statistical model, nu theta, that the set of solutions exists. So the argmin is on empty. And also the estimators are consistent, because when you increase the number of samples n, then it gets closer to the parameters that generated the data. So this is good news because it brings more theoretical guarantees to generative models that were based on Slice-Wasserstein estimators. And we're also able to show this central limit theorem under some additional assumptions, including well specification of the model. So basically, we're able to characterize the asymptotic distribution of the estimators and also the rate of convergence, the speed of convergence. And so the speed of convergence is square root of n, where n is the number of sample. And so what was interesting for us was not so much the shape of the asymptotic distribution, but mostly the fact that the rate doesn't depend on the dimension, because this is valid for any d-dimensional spaces. And if we consider minimum Wasserstein estimators, which have been studied before, so the central limit theorem, an analogous central limit theorem was derived just for d equal 1. And it was conjectured that the rate will depend negatively on the dimension of the data, because the Wasserstein distance is known to suffer from the curse of dimensionality. And so if we use Slice-Wasserstein distance, we escape this curse of dimensionality thanks to the one-dimensional random projections. And so we have a rate that is independent from the dimension. Okay, there's another property that we studied, which is sample complexity. So sample complexity, this is an important property in statistical applications, where basically you want to compare your two distribution, let's say alpha and beta, which are continuous. But what you have at hand is just a finite number of samples from them. So what you can do is evaluate the distance between the empirical approximations of these measures. And so the sample complexity refers to the speed of convergence of this empirical approximation to the ground truth, so the distance between the continuous distribution. And so for the Wasserstein distance, it's known to have an exponential dependence on the dimension. So you see that as you increase the dimension of your distributions, then the speed of convergence degrades, so it becomes slower and slower. And this is an exponential dependence, so it's not ideal. But then when it comes to a Slice-Wasserstein distance, whatever dimension is, you will obtain the same speed of convergence. And so this is, again, an evidence that this is more robust to the data dimension. Okay, so these were some results that we obtained regarding slicing the regular optimal transport problem. And more recently, we got interested into the unbalanced optimal transport problem. So I will start by a couple of reminders on this framework. So as I said in the beginning, the optimal transport problem is formulated such that you have a mass conservation constraint, which is expressed through the set of couplings that we optimize over. And so it's not necessarily robust to outliers. It cannot compare naturally arbitrary positive measures. And so a way to circumvent these issues is to use the unbalanced optimal transport problem, which was introduced by Matthias Leo, Alexander Mielke, and Giuseppe Savare. And so basically the idea is to replace this hard mass conservation constraint by this soft penalization. So the coupling, the marginals of the coupling are not enforced to exactly match the input measures, but they are encouraged to be close enough. And so this close enough is measured in terms of phi divergences here. And so depending on the choice of the entropies, phi 1, phi 2, you can get different types of matching with this unbalanced OT framework. And you can also add a coefficient rho that we can call the characteristic radius. that will also help calibrate the importance of the regularization for a given phi divergence. Okay, so it's been shown in the same paper that there is a dual formulation for unbalanced optimum transport and strong duality holds. And so for that, we need to introduce the Legendre transform of the entropy. And so basically the unbalanced optimum transport is equivalent to maximizing over a pair, so finding the pair of potential F and G that maximize this functional D that depends on the Legendre transform of the entropies and the input measures. And so there's an observation that was made recently by Thibaut Séjourné, François-Xavier Viala, and Gabriel Perret in 2022, which is the following. So unbalanced optimal transport is not invariant to translations. And so it means that we have this. So if you translate your potentials, F and G, by parameter lambda, then you don't necessarily, you can have like this non-inequality. And so it can be a problem from a computational perspective, as they discuss in their paper, because, for example, they consider a specific algorithm to solve this problem. And they showed that the error that you make at each iteration will scale linearly with the translation parameter. And so depending on the value of this parameter, it can, the convergence can be very slow. And so they develop in the same paper a workaround that is based on a translation invariant dual, and that I will explain in more detail in a couple of slides, because this is also this strategy that we will use in our contributions. And why? Because they showed that thanks to this translation invariant dual, you can actually derive an optimization procedure that is based on Frank-Wolf strategies, and that is efficient in one-dimensional problems. Okay, so it's also hard to solve unbalanced optimum transport in high-dimensional settings, just like the balance case. And so because of the work that I mentioned just here, where you have an efficient optimization problem in one dimension, we naturally wondered what would happen if we have a sliced version of an unbalanced optimal transport. And so there's different ways of combining the two constants. We propose two strategies. So the first one is called sliced unbalanced optimal transport. And so I think it's quite natural to think of this definition, given the definition of Wasserstein. So the idea is simply to use the same slicing operation, but then the divergence, the distance that you sliced, is not the Wasserstein distance, but it's the unbalanced optimal transport framework. Okay, so here you see that the penalization of the coupling is on the random one-dimensional subspaces that you define through the direction theta. Okay, so this is one way of formulating a sliced version of unbalanced OT. There's another way that we thought about, which is this one. So basically, there's a property that I haven't mentioned until then, which is that if you, like, let's erase the S letter on both sides, then this is a property that is known for unbalanced optimal transport. You have this equivalence, okay? And so what we did to define a sliced version of this is to add the letter S on both sides. Okay, so that defines a second way of merging the two constants. And because we were very inspired, we called it unbalanced sliced optimal transport. Okay, so that defines two different ways of defining the sliced version of unbalanced OT. And you can see from the definitions that they differ from a conceptual level, because as I said here in this first formulation, you penalize on the random one-dimensional space. But here the penalization is on the original space. So there's a global penalization. And because of that, they have different behavior and also different theoretical properties. So in terms of theoretical properties, we showed that so these problems are well defined in the sense that the solutions exist for both problems. And we were able to show that this sliced unbalanced OT is a metric, provided that the metric here, provided that the unbalanced OT object that you slice is a metric on one-dimensional spaces. So basically, you lift the metric properties from one dimension to multidimensional spaces through this slicing procedure. For unbalanced slice OT, it was more complicated. So we were able to show that all the metric axiom holds except for the triangle inequality. So we don't know if it holds actually. So this is still an open question that we're not able to answer. So we got interested in the duality formulations of these two problems. And so I just recall the definition of the unbalanced optimal transport problem in RD with the primal problems and the dual problems. And so it's expressed in terms of this functional here that I recall. And so we're able to show that if you consider the first formulation of our problem, so sliced and balanced OT, so this is the primal problem. And then the dual formulation is given by this formula. So it's quite intuitive because, as I said, sliced and balanced OT can be seen as basically projecting and solving unbalanced optimal transport in random one-dimensional subspaces. And so it's quite intuitive that here in the dual, you see that you basically average the dual functional for a balanced OT, but on the projected measures. Okay, so for the unbalanced sliced optimal transport formulation, so the primal problem is recalled here. And our derivations show that we also have strong duality, and the dual formulation is given by this formula. Okay, so you see that it's slightly different. So they all depend on this functional D, but they are evaluated with different potential FG and input measures. And so here, because we perform a global penalization, then the functional is evaluated against alpha and beta, and the average is inside the functional. Okay, so once we had this dual formulation, we were quite happy because our goal was to have objects that could be applied in practice and that could be computational and interesting for solving some high-dimensional applications. And so what we did is to apply the same recipe, basically, as in the paper by Thibaut Séjourné, Vialer, and Perret. And so this is based, as I mentioned, on the Frank-Wolf algorithm. So just a brief reminder on Frank-Wolf algorithm. This is a first-order optimization algorithm that is used to solve this constraint optimization problem. So the goal is to minimize a function h that is convex and differentiable on a set x that is compact and convex. And so it's an iterative algorithm, meaning that we have this first step of initialization. And then at each iteration, what you do is that you solve a linear approximation of your problem that is basically obtained with a first-order Taylor approximation around the current iterate. And then you update. And you iterate, and you return the final iterate, basically. So this is the general formulation of Frank-Wolf methods. And so when it comes to applying it to solve unbalanced OT problems, and so in particular our slice versions, then this could be convenient because if you compute the linear oracle, so basically if you compute this gradient, you can see that actually the unbalanced optimal transport boils down to a balanced optimal transport problem. And so because we slice everything, it means that we solve an optimal transport problem on one-dimensional spaces, and so it's easy to do. So this is quite convenient, but the problem is that the constraint set over which we optimize is a priori not compact because of this lack of translation invariance. So the iterates might not be well defined, and the Frank-Wolf algorithm, as it is here, is not directly applicable to solve these problems. Okay, so to overcome this problem, so as I said, we use the same recipe as was done in prior work, and we define a translation invariant dual. So this is the methodology that is detailed for slice and balance OT, but we were also able to develop such a method for the other way around, but I will just detail this one for sake of clarity. So the translation invariant dual is defined as follows. So we maximize, so we find a pair of potentials that maximize this functional, but the functional here is slightly different from the dual of that I presented until then. Because here, what we do is that we consider the same functional D, but evaluated between translated potentials, and we retain the translation parameter that maximizes this. And so by doing that, we obtain a dual that is invariant to translations. So this is something that you can show that you still have strong duality and that you have invariant translation because of this supremum operation, maximization operation. And so if we consider the iteration of Frankfurt algorithm, then this is formulated as follows. We want to solve this linear approximation of our problem. So we want to solve the dual problem. And so here we consider the gradient of the dual that is invariant to translations. And so if you write down the derivations, you obtain this thing, which is basically the dual formulation of an optimal transfer problem, balanced. And why do I say balanced? It's because here, the measures that we obtain, they have the same mass. So this is something that we show in our derivations. And so they are obtained naturally by basically writing down this derivation. And they have a closed form formula that you compute, and that depends on the entropy of the regularization that you use in your unbalanced OT problem. And so this is convenient, as I said before, because it means that one iteration in Frank-Wolf algorithm used to solve our problem means solving a certain number of optimum transfer problem between normalized measures. And so everything is in one dimension, so it's easy to do. So it consists in sorting the samples. So overall, the computational complexity of the methodology scales in this. So we have the maximum number of iterations, the number of projection directions k, and then the cost of solving optimal transport in 1D. Okay, so I'll just maybe let's conclude the day with like a nice application. So this is color transfer. So this is a classical application in image processing. So we're given a pair of images. So let's say that we're given these two images, and the goal is to transfer the color distribution of this image to the first one, and same thing here. And so until then, because the images are of size this is quite a high scale problem. And so applying the optimum transport based methodology is quite costly and out of reach. And so one way to deal with it is to maybe summarize the distribution of colors by using a palette so that we reduce the dimension. But then you might lose some information and details about the colors. And so instead here, what we did is to consider the full color distribution and use a slicing methodology. So here the third column is the result that we obtained by using Slice-Wasserstein. So not the unbalanced version, but the regular one. And so we see that we obtain some undesirable things that are called color bleeding. So for example, you see here that the green of the trees are in the sky. Here, this flower red is on the face. So maybe you want to ignore some colors and ignore some outliers in the distribution. And so this can be done by using unbalanced version of our problem. And so this is what we obtained in the fourth column. And so it required some tuning. For example, the raw coefficient that I mentioned in the beginning should be properly tuned. But then we were able to basically have an image that is cleaner in the sense of we were able to remove some color bleeding. And so this is confirmed by, for example, these maps where here you see that the flower was discarded. So there was some mass destruction here. And this is thanks to the unbalanced version of optimal transport. Okay, so I conclude my presentation by mentioning some topics that I haven't talked about during this presentation or haven't explored yet, and which I think are interesting and are around slicing. So I want to mention that there is several generalization extensions of Slice-Wasserstein distance, which mostly come from the machine learning community or like people interested by practical applications. And so they consist in tweaking a little bit the definition of Slice-Wasserstein distance and, for example, changing the distribution of the projections. And the thing that is missing, I think, in the literature, and I think it's because it's a hard problem, is that we don't know what happens in theory with this generalization. It wasn't really studied. So, for example, what happens if we consider nonlinear projections, or if we sample the projections in a non-uniform way. So this is still some open questions. And it would be interesting to answer them, because it's been shown in this paper that if you change a little bit the definition of slave association distance, you can obtain better results in practice. But it's still like a trial and error effort to know what kind of distribution you would use for what applications. So it's a bit like cumbersome to do this trial and error thing. A second open question is, how do we define a transportation map or plan with slice optimal transport? Because actually we lose this definition by the way it is defined in the slave association distance. And so there are some very recent work that take inspiration from the slicing operation to define transport maps in d-dimensional spaces. And so this is very recent. So again, some theoretical properties are unknown. So for example, the stability of such maps wasn't explored yet. And then a last topic, which I think is really interesting, but also really hard, given what has been done already, is about gradient flows. So I haven't really considered the dynamics of slave association distance in my work until then. And so it's still an open question to know what kind of convergence guarantees we can obtain with flows defined with the slave association distance. So for example, you can think of slave association flows, which means that we perform a flow in the association space, but the energy that you minimize is the slave association. And so very recently, there's an article exploring this problem, and it gives some answers to this question of convergence, especially in the Gaussian case, and showing that the map that you obtain, so the flow map, is not optimal in the sense that it's not an optimal transport plan. But there's still some many open questions when you consider general measures. There's also the problem of considering gradient flows in the slave association space and not the association one. And so it amounts to understanding the geometry of slave association space, which happens to be very hard, as demonstrated in this paper that was already mentioned, for example, by Hugo today. And so basically in this paper, they say, among many other things, that the slave association space is not a length space, and that for certain class of measures, you don't have this equivalence between the slave association flow and, sorry, the flow in the slave association space and the flow in the association space. Yeah, so I think for me, these directions are really interesting and not explored yet. And so especially when it comes to some applications like generative modeling or machine learning, it would be quite interesting to have more theoretical insights so that we can understand more what's going on with these algorithms that are black boxes. Yeah, so I'll just conclude by listing the publications that I talked about throughout this presentation. And yeah, thank you for your attention.
Thank you very much. Do we have questions? There are a couple. Let me start with the back.
Thank you for the talk. I wanted to ask, does the degree of the unbalanced slice or slice unbalanced Wasserstein distance have any significance in the performance of the algorithm when you use it in machine learning tasks?
As compared to what?
The order of the Wasserstein is what I mean. Is there an intuition if it is better to use a Wasserstein 1 or a Wasserstein infinity in performance? Yes.
I think in this application, usually people use order 1 or 2. So this is what we did 2. So this one is order 2. So we haven't explored like the influence of the order on it. Yeah, so don't have any clear answer.
So thank you for your talk. Just a question about the invariance of unbalanced optimal transport that you mentioned. I was convinced that it should be better not to have this invariance. Why is a problem for computation?
So
translation invariance.
Yeah. Yeah, so basically in that paper, they showed that, Okay, so they consider a slightly different problem because they add an entropic regularization. So like it's a synchron version basically of unbalanced OT. And then they apply synchron to solve the problem. And they showed that so you consider ground truth, which is F star G star, that maximizes your dual. And if you consider the iterates that you obtain at each iteration of your synchron algorithm, you can see that there are so the error between the iterates and the ground truth scales in something that depends on lambda. And so this is basically the speed of convergence of your algorithm. And so because it scales linearly in lambda, so if lambda is very high, then it means that the convergence is very slow too. So that's the example that they give in this paper.
Other questions or comments? Well, if not, let's thank Kimia once again and all the speakers of today.